Okay, good morning, everyone. I'm David Spears. I'm chair of the Committee on Earth Resources, which is a standing committee of the Board on Earth Science and Resources at the National Academies. We welcome you to the fall meeting of the National Academies Committee on Earth Resources. To start, I'd like to acknowledge that this building of the National Academies is physically housed on the traditional land of the Piscataway and Acotchtank peoples. We honor with gratitude the land itself, the people who have stewarded it, and the enduring relationship that exists between these peoples and nations and this land. I'd also like to review our expectations for conduct. The National Academies is committed to fostering a professional, respectful, and inclusive environment where all can participate fully in a harassment-free and discrimination-free atmosphere. We look to each and every one of you to be a partner in this commitment by helping us to maintain a professional and cordial environment. For a bit of background, the National Academies is a nonprofit, nonpartisan organization that provides independent, objective advice to inform policy with objective scientific findings, spark innovation, and confront challenging issues for the benefit of society. The Committee on Earth Resources is a standing committee and is responsible for developing activities on Earth resources and providing a forum for the exchange of information among the Earth resources community. The members of this committee are shown here on this slide, and I invite you to look online for the member bios. And you can see that we represent a broad cross-section of the Earth resources community. We all have day jobs, and we serve on this committee as volunteers. The topic we're focusing on today is advancing geothermal energy. Geothermal energy is a promising source of global 24/7 carbon-free affordable power and heat. But despite this and its ability to produce significantly more power from a smaller footprint than many existing renewable energy technologies, barriers to widespread geothermal development still remain. Advancing geothermal energy involves addressing technical, economic, and regulatory challenges to fully leverage its broad range of capabilities. In this meeting, we'll bring together experts to discuss these challenges and future opportunities to advance these efforts. So we're just going to go ahead and jump into our presentations. And we're a little ahead on time, but that's not going to hurt us. It might help us later on in the day. Our first speaker is Rita Okorafor, a Committee on Earth Resources member and also an assistant professor at Texas A&M University. She will be overviewing the current state of geothermal energy and also moderating the first panel. Rita?
Hi, everyone. Good morning, good afternoon, good evening, depending on where you are. I'll be moderating this panel, the panel that's going to be coming up soon. But before that, I want to just prepare a background. I understand that many of the people who have joined may not be experts in geothermal energy, and we're going to be listening to the experts. So let's just put all ourselves on a level playing field. My agenda is to go through an overview of what geothermal energy is. We'll look at the current energy status outlook, the evolving use of geothermal energy, and where it fits in the overall energy mix, including the fact that we have a high renewable portfolio these days. So about geothermal energy, geothermal energy comes from the word geo for earth and therme for heat, and it tends to represent heat coming from within the earth. So the geothermal energy, as we see, is formed by radioactive processes within the earth crust, releasing a lot of heat. And from within the center of the earth, this heat tends to go upwards towards the crust. So if we're coming from the crust down towards the core of the earth, we will see that the temperatures are getting higher towards the very core. Geothermal energy is considered renewable because the processes that are going on at the center of the earth, where you have the core, is ongoing, and some had started billions of years ago. So we still have lots of heat in the center of the Earth. So key things for us to realize is that it's always there. The heat is always there. More of the challenges is how do we try to harness this heat? Because the deeper we go, we'll find more heat. In some areas, the heat from the Earth has risen up maybe through some volcanic activity, magmatic intrusions that bring this heat more shallower than normal places. And so some areas will have more heat than others. Next slide, please. So a couple of terms we'll see. When we talk about geothermal energy, we have geothermal energy that is used for electricity generation. We also have geothermal energy used for direct use, and we have it as heat pumps. And within the space of electricity generation, we have the conventional hydrothermal geothermal energy. I'll talk about that, more deeply, but that's what we have been used to for a very long time. Usually associated with places where we have all these volcanic activities or higher temperature gradients closer to the Earth's crust. And then we have the unconventionals, which are some of the new ways in which geothermal energy is being harnessed for electricity generation, such as enhanced geothermal systems, advanced geothermal systems, and I'll also talk about them. Next slide, please. So one of the very interesting things about geothermal energy is its wide range of uses. It has wide applicability. So we can see that it's not only electricity generation. We can use geothermal energy for things. So on this figure that I have here on the right, we are looking at things like hydrogen production, cement and aggregate drying. We have agricultural uses, food processing, greenhouses, fish farming, heating and cooling of buildings. And all of these happen at different temperatures. So what it implies is that wherever you are, depending on what the temperatures you see within the Earth, you might be able to find a use of geothermal energy or the heat from the subsurface. On the left of this part is looking at the electricity generation aspect of geothermal energy, where we have different kinds of plants. I'll also talk about them, but this ranges at different temperatures. The higher temperatures are usually preferred for electricity generation. Next slide. So how do we harness this geothermal energy if we want to use it for electricity generation, heat pumps, direct use, and all of that? We would usually drill wells to be able to harness the fluid in the subsurface, or we would, pass fluids through certain pipes and try to extract heat from the Earth. So in the different flavors that we have of this geothermal energy, we are trying to harness them. We have to actually go in and access the ground itself, the subsurface, using wells, using pipes. And then we have the different working fluid. So the working fluid is that fluid that is going to be moving through the system, either the one that we produce directly from the ground or the one that is passing through the pipes and is extracting heat from the ground. Next slide, please. So when we talk about geothermal reservoirs, so these are where we would actually go in, drill those wells to harness the fluid that is in the subsurface, the hot fluid. Well, how did they get there in the first instance? So most likely we have water that had seeped through into the subsurface, into the ground, through pathways from the surface. And when it gets down into the subsurface, there's the heat from, things like molten magma, just, any region where we have higher temperatures or high temperature gradients. This tends to heat up the water, and then this water rises. It's heated up, it has less density, it rises. There's convection taking place. And then we find it at shallower depths than where those really very hot rocks are. So what happens is we can then go in, drill a well, access this heated up fluid that has come somewhere on the surface. And it would usually be trapped by some sort of seal that doesn't let the water come out. But on the surface, there are other indications that we might have something in the subsurface. So when we hear about geysers, fumaroles, hot springs, indications on the surfaces of steam or hot water bubbling out that would tell us that something is going on underground. Those are early indications that we have something below the earth. Next slide. So some kind of terminology you may be hearing as we move on today. We would have the word energy, and energy is simply the ability to do work. And the units you might be seeing will be kilowatt hour, kWh, BTU, joules. But when we're looking at large scales, which is often the case with geothermal systems, we'll be having megawatt hour, gigawatt hour, terajoules, and those kind of things. So that's representing energy itself. The next one is power, which is the ability to do work, or the rate at which we're doing the work or expending the energy. And usually it's in watts, but we could also have joule per second, which is energy over time. And when we're looking at large scales, we would have units like megawatts, gigawatts. Next one. So now we have some kind of ways of differentiating this power. Now, the power that is coming from, that resides within the subsurface, where we would find this geothermal resource, would be the thermal power. And so if you see a subscript TH beside your MW, that is the thermal power. Well, what we do when we pass this thermal power through something like a power plant, something that converts this subsurface power to usable power through electricity, we have electrical power with a subscript E. Next click, yeah. So the MWE. So when you see any slides talking about MWE, or you hear words MWE, we are referring to the electrical power that is being generated. And then enthalpy is a word we use quite often. It's just representing the heat content within a system. So it could actually either be in kilojoules or kilojoules per kg, or the converted form of it. Okay. Next slide, please. So when we have geothermal energy or power in the subsurface, we would usually want to use it on surface. And depending on what the temperatures are or the enthalpies are, we would have different kinds of power plants on surface to extract this thermal energy that we have from the subsurface. And so this slide shows different versions. We have dry steam power plants, and we usually have that when the resource in the subsurface is high temperature. Perhaps the fluid is in vapor form. When it comes out, when the pressure drops, it's in vapor. So it's easy for us to pass it through a steam turbine in that vapor phase. The other one is a flash steam power plant. So we have a fluid that is liquid, but when we bring it to the surface and we pass it through a flash tank, that reduces the pressure, steam is generated, vapor is generated, and we can then take that vapor, pass it through our steam turbine to generate the electricity. Sometimes the temperatures of the subsurface we're trying to harness may not be sufficient, that even when we reduce the pressure, we wouldn't be able to generate a lot of steam. And so it's going to be liquid. It's kind of hot, and it could heat up another fluid that would eventually become vapor, and that vapor can pass through the turbines. The reason why, again, we want this vapor is the turbines aren't designed for high liquid content. And so we have binary cycle power plants where the fluid that comes in from the subsurface heats up another fluid. That fluid then turns to vapor and goes into the turbine, and that's what is used to generate electricity, while the fluid that came in from the subsurface goes back through using an injection well without being exposed to the surface environment per se. Next slide, please. Now, power plants for geothermal systems. So we've seen the dry steam, we have the flash plants, and we have the binary power plants. They all have different conversion efficiencies. That is how we convert what that thermal power was, the MWTH is, to the MWE. And so based on a study that compiled data across several different power plants, the highest reported conversion efficiency is about 21%. This is generally lower than some of the other thermal power plants like solar, which should be in the range of about 30 to 40%. And it's just something for us to bear in mind and think of how can we try to be improving efficiencies. But the good thing is that the introduction of binary power plants has allowed us to go towards lower enthalpy fluids to be able to harness lower temperature or lower enthalpy fluids. So this expands the application of geothermal energy. Next slide. So other things that you'll be hearing. So we've talked about the conventional ones, and that's where we have a well being drilled into, or wells being drilled to a source that produces the hot liquid by itself. And then we take it to the surface, pass it through the plant, and we may need to do some reinjection to stabilize, to maintain pressure, and just to avoid any form of thermal pollution. But there are some times when we have a system that is very hot, but we don't often have the fluid within the subsurface that we can produce. So other ways in which we could harness the heat is to actually drill wells that go down into those hot rocks. And then we inject fluids down into those hot rocks to extract the heat from the subsurface and bring it back up. On this slide, I have the advanced geothermal systems. In this system, the fluid passes through those pipes or tubes or wells without coming in direct contact with the rocks themselves, the hot rock. So heat is transferred from the rock to the pipes, to the fluid that is inside, and brought up to the surface to generate electricity or for other uses. We have enhanced geothermal systems. In this case, we've created pathways in rocks that are not very permeable. That is, we don't have enough flow paths for the fluids to move. We inject cold fluid. It comes in contact with the rock, and then it becomes heated up, and then we produce this heated up fluid back to the surface to generate electricity, or again, any other use for geothermal energy. And so what AGS and EGS is trying to do for us is trying to expand areas in which we could actually harness the heat from the earth, even if we don't have the permeability, which is the flow path for the fluid to move, or the working fluid, which is that something, things like water or steam that we could have produced from the subsurface. Next slide, please. So what's the status, or how does geothermal energy look like globally and within the US? So globally, the last set of information we have is that we have, geothermal energy is high in locations where we have this conventional geothermal resources, such as the US, Indonesia, Philippines, and all of that. And then, next slide, please. Within the US, even though we see that geothermal energy is very high from the US globally, within the US, it constitutes a very small portion of the sources of electricity generation. So this is what we have on this slide. It's about 0.4%, but it has the potential to grow if we use it if we try to harness the resources in different ways. Next slide, please. So usually every 5 years, there's a report on the status of geothermal energy globally. And so this figure that I have here on the right is showing the trend of geothermal energy for the past few years, measured every 5 years. We can see that there's been growth, which is very good and positive, and more growth is even anticipated. So hopefully by the end of next year, we should have some more information about the status of geothermal energy. A couple of countries have added more geothermal energy. The interesting thing to see is also that the direct use of geothermal energy is growing. So this figure here is looking at the different uses over time. And we can see that across all of them, geothermal heat pumps, bathing and swimming, space heating, greenhouse, etc., it's growing, moving from as time increases. Okay. And what it also means is that we are perhaps finding ways in which we can reduce emissions. So if we are replacing electricity generation from emissions generating sources to something else, it's really helping in that regard. Next slide, please. So next slide. Beyond the use of geothermal energy for electricity generation and heat pumps, district heating, and all the other things I've mentioned, there's been growing use of or applications of geothermal energy. So one of the interesting ones is hybrid technologies, where we combine geothermal energy with another source, like let's say solar energy. Now, solar energy might be, it's an energy resource that we have very high in the daytime, and maybe in the night we don't have, and geothermal energy could complement that, okay? We have things like lithium production, desalination. We have thermal storage, chemical mechanical storage using geothermal energy concepts. And we have things like direct air capture CO2 sequestration, where geothermal energy is used to regenerate the adsorbents or even absorbents used for extracting CO2 from CO2 sequestration systems. More importantly, we are thinking about green hydrogen, and geothermal energy is something that could be used for to convert water, split water through electrolysis to generate hydrogen. So the use of geothermal energy is far-reaching. Next slide, please. Well, this is an example of a combination of geothermal energy and solar energy together. This one is in Nevada, and it's just, like I said, to try to balance when we don't have a lot of the solar energy, we have the geothermal energy. And so it fits right into many of these places to complement the energy resource. Next slide, please. So let's see where geothermal energy is within the energy mix. So on this slide, I show the capacity factors of different energy systems. So capacity factor as a word is trying to determine, like how long do I have this energy system on over a given period of time compared to what it's supposed to be doing in terms of output. And so what we see is that geothermal energy has a very high capacity factor. It's very reliable. It's something that is on most of the time. To use an example or to compare it with, let's say, solar energy, just for illustration. So if I have my solar energy more during the afternoons and in the evenings, I don't have it. I'm having about 50% capacity factor. Whereas for geothermal energy, I have it full, all through the period of the day. So we see that it's something that could be a base load, which means it's something you can rely on for minimum energy requirements. Next slide. In terms of life cycle emissions, this is where geothermal energy fits within other energy resources, depending on how the life cycle assessment is computed. But currently what we see is that the CO2 emissions equivalent, CO2 equivalent is quite low for geothermal applications compared to some other energy sources. Next slide, please. In terms of land use, which is how much space or how much land we need to use for geothermal energy or any other source of energy, geothermal energy, it's somewhere on the low side compared to all of them. Okay, so we see this also as an advantage, and I'm sure you'll hear more about it as we move further on in our panel and our discussions. Next slide. And ultimately, the levelized cost of energy, which is looking at the cost of energy per megawatt hour. Geothermal energy fits somewhere right down below, which is this red curve that we have on this figure. And over time, I'm sure this is something that could be driven down much lower as we bring in more advanced technologies. Next slide. So I would summarize by saying that we've seen geothermal energy. It's something that is reliable. It's renewable, depending on how we manage our resources. It has high capacity factor, low footprint, but my favorite about it is its diverse use. It's not only for electricity generation, and we could harness different ranges of temperature from the resource. There are indeed some challenges that we see. I'm not going to preempt you all of them, and I'm sure some of you have some in mind. But one of the things is it's traditionally believed to be a resource that is location specific, which means where you have the resource, that's where you're going to generate it and most likely use it. So you put your plants there. We've seen the efficiency, which is conversion efficiency from thermal power to electrical power. And when we start moving into the advanced geothermal systems and enhanced geothermal systems, we are using additional working fluids, which requires more resources than originally we would have for conventional geothermal systems. One other thing is it does have large upfront investment costs because you need to put together your power plant, your systems, or while drilling after drilling your well. So everything needs to be in place. So which could be some challenges. But as we go through the panel, we would hear more, and we look forward to your comments and questions. So thank you all very much. And let's take a deep dive into geothermal energy. Thank you. So what we're going to do now is we're going to listen to the different panelists that will talk about their different technologies where they have so much expertise is. The first person we would hear from will be Paul Thompson. Paul is the Vice President of Business Development at Ormat Technologies, Inc. Welcome, Paul.
Thank you, Rita. Okay, great. Well, thank you all for having me today. It's an honor to speak to the National Academies. As Rita explained, my name is Paul Thompson, and I'm the Vice President of Business Development for Ormat. I have been told I have 8 minutes to tell you everything I know about geothermal, so it's going to be hard to do, but I'm really going to focus on the innovations. And you're going to hear later today from folks who have lots of technical innovation, and I'm going to talk a little bit about the market, the demand, and how that's opening up more revenue and a bigger margin for the advanced geothermal technologies and so forth that you'll hear about later today. So with that, if I can go to the next slide. Ormat has about 60 years of experience. Today, we operate 1.4 gigawatts of generation around the world. And what makes us unique is that we not only operate our own power plants, but we sell equipment to third parties. So we have equipment in 31 countries around the world. And why are you listening to me? I'm our Vice President of Business Development. I served as chair of the Public Utilities Commission in Nevada that has the largest geothermal deployment per capita of any state in the country. I served as the governor's energy advisor in Nevada and have worked at some law firms and for some United States senators and so forth. So thanks for the time. If we move to the next slide, we'll highlight kind of Ormat's footprint. So today we are the largest geothermal developer in the US. We are constantly kind of deploying innovation. And what's so exciting is that, after kind of 20 years of work here at Ormat, we are seeing markets recognize geothermal for being able to supply three things. One is energy, one is renewable energy credits, and the third, and maybe most important, is capacity. For decades, the geothermal industry was explaining that as you try to move to greater renewable penetration, when a bigger part of your market is renewable, you have to have capacity, meaning, solar and intermittent resources are great, but how are you backing them up? When the sun doesn't shine, what do you do? And so California was a great example. We saw California deploy almost 30 gigawatts of solar in the last decade, but they didn't pay attention to capacity. And what did that lead to? Brownouts and blackouts. And so I'll talk about it on a later slide, but California recognized, look, we need carbon-free capacity. And if there's anything you remember from my presentation today, it's that geothermal provides carbon-free capacity that's reliable there, and as Rita hinted at this morning, has zero emissions. We go to the next slide. We're going to talk about this increase in demand. So if we go one more, regulations have really moved geothermal to this exciting time. And I have to say, in my 20 years, this is the most exciting time I've seen for geothermal because we can focus on this 2 gigawatts. California, after its brownouts and blackouts and realizing that it didn't focus on carbon-free capacity, said, we have to get 1 gigawatt of geothermal for all, a pro rata share for all of our load serving entities. This was a lot of work done by the geothermal industry to say, look, in your modeling, what we can prove is that 1 megawatt of geothermal energy replaces the need for 3 to 4 megawatts of solar with integrated storage. I want that to sink in because that is so incredibly important in this discussion when we talk about energy density. Because geothermal produces power 24 hours a day, 7 days a week, and can ramp up and ramp down and do all these great things with hybrid power plants, as Rita described, 1 megawatt of geothermal can replace 3 to 4 megawatts of solar with integrated storage. So when you start evaluating the costs of solar with storage, you got to multiply it by 4 to see if it's competitive with geothermal. If you look at the environmental footprint of solar with storage, you got to multiply it by 3 or 4 to compare it to geothermal. And when regulators figured this out, they said, it's a no-brainer. We need as much geothermal as we can get our hands on. And so we saw the valuation for the capacity go up, and power purchase agreements start getting signed. I'd be remiss if I didn't talk about the states having renewable portfolio standards and obviously state incentives for tax abatements. And then finally, the federal government and the big tax credit in the Investment Reduction Act really helped put geothermal on a level playing field with other resources. If we go to the next slide, you'll see that the demand for electricity is also going through the roof. Unless you've been in a cave for the last, I don't know, year, you hear about hyperscaling, these data centers, and the need for electricity. You've seen the push for electric vehicles. We've seen the retirement of high emitting fossil resources. So the demand has just been increasing tenfold, and we need to get geothermal moving in the same direction to try to keep up. Next slide gets us to kind of focusing on innovations. So in this slide, the kind of key things you need for geothermal development, you need to be able to get land. You need to be able to permit it timely. You have to be able to interconnect it to the grid with transmission and interconnection. You have to be able to find that geothermal resource and then strike that power purchase agreement. If we had hours this morning, I could walk you through each one, but I'm just going to focus on a couple. So the next slide here shows when we are trying to find that geothermal resource, the industry has really improved. Here's an example that Ormat operates in 28 different geologic fields. So that means whether it's a volcano in Hawaii, the basin and range in Nevada, continental spreading in Iceland or Kenya, we've been able to develop successful geothermal projects. If you can bring heat to the surface, the geology and the innovation in that sector are allowing us to convert that to electricity. We have 4 current developments going on today and 40 exploration projects around the world. So again, the ability for the industry to get high power purchase agreements is allowing us to expedite exploration, development, and operation. The next slide, I think, is going to start discussing exploration. So this arrow from left to right I'm gonna call it greenish, bluish, teal. Kind of shows you the development of geothermal. You start with your geoscience and trying to determine which land you want to look at. You go into exploration, project construction, and then you get to manage the reservoir into perpetuity if we do it right. But that exploration component is key because that has required lots of permitting and lots of discussion that has really slowed geothermal development. In the next slide, one of the great improvements we have seen is that in the US last year, we tried to shorten those permitting timelines. So you're here to hear about kind of cool innovations with turbines, and you're going to hear about drilling techniques and closed loop systems. I'm going to bring you back to kind of the lame, boring innovation, which is the federal government said that to get an exploration permit, to be able to drill a full-size well and go determine if there's a geothermal resource, instead of taking 3 to 4 years, can only take 12 months. Now, this number is a little deceiving because they can still require baseline studies ahead of time, but that is a huge improvement if you are trying to find geothermal resources in the US on federal lands. This third column here talks about the utilization EA. That is the permit for the power plant. And again, that was taking between 2 to 4 years to get that permit. Again, the federal government in the FRA, the Federal Fiscal Reduction Act, limited this to 12 months. So these kind of two benign regulatory changes to NEPA were huge. And I think, to be determined what the new administration is going to do for permitting. But if we can shorten that permitting timeline, that will allow us to deploy gigawatts of geothermal moving forward. And that's echoed in the Department of Energy's geothermal report from a few years ago. Next slide takes us to drilling innovation. So Ormat recently signed a alliance agreement with Schlumberger. Ormat is vertically integrated. We design and manufacture our own equipment. We drill our own projects. We construct and develop them ourselves and negotiate the power purchase agreements. But with this increase in demand, we frankly have reached our capacity for drilling projects. We can only drill our own. So if you had come to Ormat and said, I think I have a resource, I would like you to, help me explore it, we would say, I'm sorry, we're completely at capacity. So we're working with Schlumberger, who is a drilling services company, to say maybe their geothermics arm or their drilling arm can go help you explore and determine if you have a geothermal resource. And the U is the royal U. It can be a C&I customer, it can be a utility, it can be a hyperscaler, to determine if you can bring that geothermal resource to the surface. And then Ormat is going to work with them to put a power plant on that, convert it to electricity, and get it to the grid. This is the first of its kind alliance between oil and gas drilling companies and large-scale geothermal, trying to provide a fully developable supply chain for third parties moving forward. I think I've got like a minute or two left, so we'll go to the next slide. We are constantly trying to improve our turbines. We just rolled out today our first 50 megawatt binary turbine and there's some words on there. It's between bearings. The design is got more turbine blades between it to be maximum efficient on lower temperature resources. We're also manufacturing our heat exchanger tubing differently to meet supply and demand and continue to improve them. If you go to ormat.com, our first geothermal power plants were very small in the kilowatt range. They grew to the megawatt range, and now we're getting into the 50 megawatt range and competing with steam turbines in this binary cycle. I think the next slide shows you the binary process for any of you who don't know it. This is the bread and butter of Ormat. We bring up that geothermal fluid. It's red. It goes into a tube and shell heat exchanger. It vaporizes a working fluid, which builds pressure. That pressure wants to relieve itself across a fancy fan or a turbine. And voila, we've converted thermal energy to mechanical. We're spinning a turbine blade and producing electricity. What Rita alluded to, I think, is critical, that this system is completely closed. The working fluid, once it passes through the turbine, is condensed back into a liquid and reused, zero emission. The geothermal fluid passes through the vaporizer and preheater. 100% of it is re-injected back into the geothermal reservoir. where it matriculates across the hot rocks, it gets its heat back, and is produced over and over and over again. So one of the toughest agencies in the world, the California Air Resources Board, has defined binary geothermal as a zero emission technology. I would invite you to go look at our YouTube page because you can see all of these types of power plants. And I think what Rita pointed out that's really critical is this technology pairs very well with flash technology. So you can cascade from a flash power plant to a binary power plant. And I think the vision for the future is you're going to have flash resources, binary resources, and EGS resources all working together to maximize the output of power plants moving forward. I hope I have one or two slides left. Power prices. Again, that demand in the market has taken power prices from somewhere around $75 a megawatt hour to about 120 megawatt hours today. Why is that margin important? Because that allows companies like Ormat and all the rest of the companies you hear later today be able to deploy more innovative, costly technologies to bring that resource to the future. When prices are really reduced, we can't drill as deep, we can't deploy EGS technologies, we can't use 3D seismic because we have to make that, we have to pay for all of that in a long-term power purchase agreement. So seeing those prices go up will increase geothermal development, it'll increase the innovation moving forward, and it will really push geothermal to the next level moving forward. With that, my time is up. I want to thank you all for your attention and be happy to answer any questions you may have.
Okay, thank you very much, Paul. We will listen to Greg. So Greg LaVille was a chief technology officer at ConocoPhillips, and he'll be talking on enhanced geothermal systems. So Greg, I invite you to speak.
Yeah, thank you so much, Rita, and thanks to the National Academies for allowing me to participate in this webinar. I've been given 500 seconds to talk to you about a topic that really deserves hours and hours of conversation. So I'm only going to be able to focus in on 4 aspects of the EGS story. And what I particularly want to talk to you about is, firstly, some of the amazing results that have recently been achieved as far as driving down costs and increasing the output of the system. So on this slide here, I've got 3 portions to the panel. If you look at the graphics on the far left to start with, what you see is a story here about bringing technologies from the oil and gas industry into the geothermal space and being able to dramatically reduce the time and cost of drilling wells. So if you went back just 4 years to 2020, the average time it would take to drill a well down to a depth of around 12,000 feet measured depth was somewhere in the 100 to 150 plus day range. But then at the Utah Forge project, which is a US government funded test site out in Utah, some very innovative technologies were applied that basically cut the drilling times in half. I'll tell you some more about those technologies in a minute. Following on from Utah Forge, a company called Fervo Energy was able to take that same suite of knowledge and skills that were developed there and apply it at another project in Utah called the Cape Project. And they're now drilling wells to these types of depths in less than 20 days. And this is all really exciting, but when I look at what is possible in the future, one of the things that really is really encouraging here is that if you look at what the oil and gas industry is doing with drilling wells, we're drilling wells to those types of depths in less than 10 days. So there's probably some really significant further improvements, and I'll talk about some of the technologies that have moved the needle to date and could move the needle in the future. One of the things which has really made a difference is the story in the middle panel. Traditionally in geothermal, the wells that have been drilled have been vertical wells. They're tapping into hot rocks in the subsurface, and they're trying to bring that hot fluid out of the Earth's crust and bring it into a power plant or use it for some type of direct use. What's happened recently is the drilling technologies that have allowed the oil and gas industry to drill horizontal wells and hydraulically fracture them and dramatically increase the production of oil and gas in America have been applied in the geothermal space, once again by a company called Fervo Energy. What you see here is the progression. Prior to 2020, nobody had successfully drilled a horizontal lateral in a geothermal field. And this is really important because by drilling horizontally, you get more exposure to the rock. It's what's unlocked, as I said, the very tight oil and gas resources that are the focus of America's oil and gas industry today. And you can see the first well there was about 1,000 meters long, 3,000 feet. But now the Cape project, the length of the laterals have been increased to around 5,000 feet. But once again, when you look at what is being done today in the oil and gas industry, there is an enormous amount of room for further improvement. Today, we very easily drill wells to 2-3 miles. In some of the basins, we're drilling 4-mile long laterals. So by increasing the lateral length, I'll talk about this in a few minutes, but you can increase the thermal longevities of projects and do a lot of things to really improve the economics. And then finally, in the panel on the far right, another really important part of the story is what type of flow rate you're getting out of the ground. So Rita talked about the importance of capturing the heat, and you need to bring the heat to the surface with a large volume of fluid, because the efficiency of the power plants today is really not as great as you'd like it to be. So the story here is once again of improvement. If you went back to the pre-2022 period, you were looking at something less than 10,000 of barrels of water or fluid being produced per day per well. You can see the progression there. Today, we're up to a number around 70,000 barrels of fluid a day. And once again, in the future, we're looking at ways where we can dramatically increase that. So that's going to get more heat out of the ground per well, dramatically improving the economics. Brian, if we get in the next slide. So how did we do this? If you look at the industry, the innovation, a lot of the recent innovation, at least in the subsurface, has been by a process of applying technologies that have been perfected elsewhere, perfected in the oil and gas industry, to the geothermal space. So in this slide, I have two halves to it. The left half is about the drilling story. The right half is about the completion story. If we look at the drilling story first, really on the application side is taking the modern drill rigs. So the modern high-tech rigs with computerized control systems, top drives, which allow for ultra-efficient drilling performance, and applying that in a space where, frankly, the rigs that had been being used were far less modern than what's being used by oil and gas. If you go down to the other end of the drill string, go from the surface all the way down to the drill bits, the type of drill bits that were being used in geothermal space were what we call roller cone bits. They have basically cones on them which turn and try to grind up the rock. Oil and gas industry has basically moved away from that quite a while ago. We now use polydiamond crystalline bits or PDC bits. Using these types of bits, the rate of penetrations are much faster. So you're able to drill the well much more quickly. And then tying the entire drilling package together as a system has really been an important piece of the story here about how they've been able to reduce the time of drilling from 150 days down to less than 20. So physics-based drilling, if you will, and there's been a group out of Texas A&M which has really helped bring that knowledge and that workflows to the geothermal space from oil and gas. So that's the drilling side of the story, but the completion side of the story is equally as exciting in that the types of wells being drilled today, as I mentioned, have transitioned from largely vertical wells over to horizontal wells. So if you look at the diagram in the bottom right-hand portion of the slide, what you see is a depiction, kind of a cartoon depiction of what was being done in the past. With vertical wells for an EGS system, you were trying to connect up basically the fractures generated by the vertical well with producers. That was very hard to do, because what we've learned in oil and gas is that from a single point source, like what you'd get in a vertical well, you generally create fractures which come out in a planar system. They're not a very wide plane. Trying to intersect that with another vertical well is difficult, if not in many cases impossible. So a lot of failed systems with dry holes and poor performance. However, when you go over into the horizontal system, you're creating orders of magnitude more fracture area with that type of system, and connecting the injectors and the producers becomes a relatively trivial step. You're reducing the risk, taking out the uncertainty, You couple that with the picture in the top right of a modern high-tech frac fleet, and suddenly you've got the ability to dramatically increase the flow rate of geothermal wells. So that's the story, if you will, from drilling and completions. I now like to translate that over into a bit of an economic perspective, look at power output per well. So at the end of the day, to drive down the cost and really improve the reliability of geothermal, what we need to do is maximize the output for every well we drill. And if you look at the green bars here on the graph on the left, what you see is that the power output really started out pre-2020 being relatively small, something in the 1 to 2 megawatt range. At Cape, they were able, I'm sorry, at Fervo's Blue Mountain project, which was a demonstration project before Cape, they were able to increase that gross output to around 3 megawatts. Today at Cape, it's in the 10 megawatt range. But what I'm showing there in the red bars is a very viable transition or scale up, if you will, using oil and gas technologies to increase the output per well, with something in the 20 to 25 megawatt range being very viable, just looking at using oil and gas technologies, and then going all the way to 50 megawatts if we can find ways to drill wells into what we would call super hot rocks. So rocks that are about 400 degrees centigrade in temperature, which is an effort that Tara Rogers is going to talk about here a little bit further on in this set of presentations. Also want to clear on this slide some of the elements that are really being focused on as far as science and engineering efforts. A couple of these here are the two on the far left of those boxes is around thermal output. So, you know, on the last slide I showed you, we've gone from 30,000 barrels of fluid a day at Blue Mountain to 70,000 at Cape, with the ability to head above 100,000. How do you do that? Well, you drill with larger casing, you increase the fracture conductivity, you may move the wells further apart, so you get more surface area. And then you're really trying to get into higher and higher temperatures. And this is really a part of the story, which is incredibly scalable and is already at a point where commerciality has been achieved. So I think you're going to want to watch this space because the flow rates and the heat output per well is really going up. The next two boxes talk about another element. We don't want just to have very high flow rates. We also need to have thermal longevity. So Paul mentioned, you know, these plants can run for decades and decades if you can keep feeding hot fluids into them. Frankly, that's been a bit of a challenge. That's the reason there's a gap between the actual output of geothermal energy in the US, which is around 2 gigawatts on an instantaneous basis, and the installed capacity, which is around 4 gigawatts. So we really want to focus on thermal longevity. And once again, the use of horizontal hydraulically fractured wells is really changing the game in this space. You can drill longer laterals, you can move the wells further apart. We're looking at tens of millions of square feet of surface area for these laterals. And we can improve conformance as well. The final set of boxes talk about cost reductions. I've already talked quite a bit about reducing the drilling and completion costs, so the subsurface component, but there's ways to reduce the cost of the plants. And then, of course, we really want to reduce the operating cost as well. That brings me to my last slide, Brian, if you could switch over. So what I want to leave you with is two graphs, one which has been achieved on the left in the oil and gas industry as far as output of hydrocarbon resources, and then on the right, a potential projection for what is possible in the geothermal space and why everyone should really be excited about geothermal. So those of you who have been following the oil and gas industry in the US know that prior to 2005, the industry was basically contracting. Many people thought it was dying. We were building LNG import terminals all around our coast. And then in 2005, we started applying a suite of technologies focused around hydraulically fractured horizontal wells. And you can see the dramatic improvement in production that has occurred. You heard a lot about drill, baby, drill in this last presidential election, but I can tell you since 2005, we have been doing that. And today, the US is the world's largest producer of hydrocarbons on the planet. It's helped energy security, economics, and even helped in the environmental space, as Rita showed you, by backing coal out with natural gas. But what about geothermal? What can be done as far as increasing production? We're looking at a resource today which is enormously large, can last for thousands of years, providing all of the US's energy needs. But today it's less than 0.4% of just the electricity portion of the market. Well, by applying these same technologies, there is the possibility to replicate what was done in oil and gas and dramatically improve the output from this very, very large resource. So with that, I'd like to wrap it up and hand it back to you, Rita. Thank you.
Thank you very much, Greg. You are making this very exciting for me. I can't wait to for the panel session. But then I would like to invite Janine to speak on advanced geothermal systems. So Janine Vani is the Executive Vice President for Evo Technologies. Janine, please, you're welcome to speak to us about AGS. Thank you.
Well, good afternoon, everyone. Thank you so much to the National Academies for inviting me here today. It's truly an honor to be here. And I'm going to talk to you about an advanced geothermal system called the Everloop, which is a multilateral closed-loop geothermal system. Next slide, please. So Ever's mission is to enable local clean energy autonomy everywhere. This goes back to what we just heard from Greg, that inspiring message that we can repurpose oil and gas technology to bring heat and power at the utility scale around the globe. This is hugely important to the world right now. We use the oil and gas to harness the heat. The product is completely carbon free, it's always on, and it uses very little land and water. So if we can take geothermal, make it scalable, take it outside of the niche places that we see it develop today, we can change the energy landscape. Next slide, please. So before we get started, a bit about Ever, a bit about myself first, actually. I am a geologist and I'm one of the co-founders of the company. And the first 6 years I did spend a lot of time developing our land portfolio and drilling our first couple of projects. Now I lead the corporate affairs team because, to Paul Thompson's presentation, we need to de-risk the policy and regulatory environment in order to scale geothermal. So we founded the company in 2017 on a simple bet that geothermal needs to be scalable and only closed loop is truly scalable. We have a track record of technical implementation. So we have built this Everlight pilot in Alberta. We built it in 2019. It's a closed loop system that has operated for 5 years. We built a project in New Mexico in the fourth quarter of 22, and that's the Ever Deep demonstration. We drilled the deepest, hottest directional well in onshore North America, and we innovated some new technology there, particularly the insulated drill pipe, so we can talk about that later. On the commercial side, we are developing our first project. You see a picture on the bottom there. That is our first commercial project. It's an old photo now, but we've been drilling that for over a year. We plan to have the electrons on grid next year. It's an 8 megawatt electric project. On the financial side, we've raised $450 million to date, and we have received some grants, particularly a very large grant from the European Union Innovation Fund. Without that grant, I think it would have been very hard to finance that first project. We have been talking about technical challenges today and headwinds, and drilling costs are high. We're seeing them come down, but the first of a kind projects definitely have those headwinds. So next slide, please. So this slide shows an iteration of our technological progression. So the closed loop system essentially works as Rita explained. You have a working fluid that circulates in isolation from the subsurface, so there's no fluid exchange between the surrounding rocks and the wells themselves. The heat is transferred from the rock to a working fluid as it circulates, and then it is extracted at surface through the organic Rankine cycle power plant, which Paul and Rita touched on, or through piping it into district heating or any sort of commercial or industrial heating use you may have. The closed loop system is a bit unique in the sense that it doesn't need a pump. So getting back to what Greg was touching on, this sort of nameplate capacity and the ability to be able to operate at nameplate capacity. With the Everloop, you do not need a pump, and so your net power and your gross power are very close. So you're not losing a lot of power to powering your electrical submersible pumps. So on the top left, you see the Everlight prototype. So we built that because most of our customers in Europe said, you have to build this, we have to see it work. So we drilled and connected the wells, we tested our chemical sealant, which is called rock pipe, and we proved the thermosiphon. So with that set of developments, we were able to then scale it up to what you see on right, which is the Everloop 1.0 well construction profile. So this is the well construction profile we're delivering in Germany today. And on the farthest right is the sort of pitchfork looking well construction profile. And this is what we think is going to enable geothermal anywhere. So we want to drill deeper and hotter. The goal is to be able to drill cost effectively at average geothermal gradients around the world. Next slide, please. So this is a bit of a zoom in on our technology. I'll just turn on my, oh, I can't point. Never mind. Okay, so we have two vertical wells that are drilled simultaneously from the same pad site. So you see the red and blue sort of vertical wells. Those are drilled simultaneously. They're completed according to whatever your local environmental regulation is, with standard casing and cement. And then when you get down into the bottom where you're turning horizontal to drill your multilateral wells, we set an intermediate casing point and we drill out these multilateral wells. I see that I've got a question here we'll get to at the with a Q&A period at the end. Once we drill out the multilateral wells, we connect them toe to toe, and that's connected using a anti-collision technology called magnetic ranging. And we've used that commercially at Garrett's Reed, and we've used that in Everlight. So we're able to connect 6-inch well bores under the ground, 4.5 kilometers deep. And once we connect the wells, the loop is effectively closed. Once the loop is closed, we pump down the chemical sealant and we seal off the lateral sections. So the chemical sealant acts like a steel casing would. And so we've hermetically sealed off basically these pipelines now from the reservoir. Once that's done, we truck in water. It has biocides and corrosion inhibitors in there, but otherwise it's fresh water that's injected down the injector well. It goes along the multilaterals, heats up and goes to surface hot. So that's basically how the system works. What are the challenges with closed loop? Well, conductive heat transfer is slow. So you need to drill a lot of wells to increase the surface area to be able to harness enough thermal energy out of the ground. So that's, I think, one of the big differences between hydrothermal, EGS, and closed loop is the number of wells you need to drill to get the same thermal output out of the ground. So on the right, you see how we differentiate from other systems. It's closed, no need for permeable aquifer. It's driven by a natural thermosiphon. There's no fracking required. Induced seismicity, I'm a geologist, so I have to say, anyone can cause induced seismicity if you are to drill into a critically stressed fault. So you do have to do your proper due diligence and geohazard assessments, but by and large, it's a very, very tiny chance of causing any induced seismicity. There's no carbon emissions or greenhouse gas emissions associated with the production of the energy. There is obviously carbon in the supply chain, but not in the production of the energy. Very minimal continual water use. The operating expenses for closed loop, this is a huge difference from other types of geothermal. It's 80% less because we're not moving water around on the surface. We don't really have a very big power plant. Having said that, we do have that large capital outlay on the forefront to drill all of the wells. So it's just a different way of designing the geothermal, the picture. There is a very low thermal output risk or uncertainty, and I know this is highly debated in technical circles about the cooling of geothermal, closed loop geothermal multilateral wells. So you have to do very good fully coupled well bore simulation models. So you need to couple your subsurface to your facility. And then that dictates your well spacing. So if you space your wells properly, you have the right length of lateral well, and you flow it properly, you should be able to maintain and not cool those wells for a very long period of time. So these are generational assets, but I will say that it has to be managed appropriately. So I think that's where some of the modeling needs to be improved, some of the third-party modeling that's out there. Project life cycle obviously depends on regulatory, but in Germany, we were permitted in less than a year. So we were able to get up and running pretty quickly. I think in the US, we would project 3 to 5 years for permitting, but we've seen from Paul's conversation that there has been a lot of amazing work done with the Department of Interior and the BLM on their categorical exclusions to sort of help us get these projects moving quicker. Next slide, please. So now I just wanted to talk about environmental attributes of the technology and basically all geothermal. So this slide is showing the emissions and materials intensity for power generation. So on the bottom, you can see the different forms of power generation: coal, gas, ever/geothermal sits in the middle, wind and solar on the right. The the orange bars are showing you the emissions intensity in kilotons per terawatt hour. So as Greg said, you know, we have sort of cleaned up the emissions profile by backing out a lot of coal um, and building more gas, but we can do better with geothermal. Wind and solar obviously has no emissions intensity, but the materials intensity, which is the blue bars, is showing you the mining tail associated with wind and solar. So the point of this slide is to show that geothermal, ever is included in the equation here, it really shines because it has a low minerals intensity and a low emissions intensity. And the supply chain is for the most part local. It can be made in America. So this is one of the, I think, things we really need to think about when we talk about growing the geothermal landscape in the US. Next slide, please. So we have, this slide is showing the life cycle water consumption for different technologies. Rita touched on this, so I think I can skim over it pretty quick. But basically, geothermal is very good with respect to other technologies. The Everloop requires water for drilling, but almost none in the operations. And I think the EGS systems recycle 80% of the water. So that bar should probably drop down. I'd have to check the statistics on this. And a lot of the NREL published data is quite old now, so I think it would be really great to see new numbers. And hydrothermal uses water basically for voidage replacement. Next slide. So on the land side, a picture is worth 1,000 words. We can see a very large wind farm, a smaller sized solar farm, and then the geothermal picture in the bottom left. All geothermal is pretty much built under the ground. So this is another reason that there's a really high value proposition for geothermal. Land is a premium, landscapes are a premium. So this is really important. It's better for the environment, it's better for wildlife. So for the same surface land use, Everloop can generate 35 times more power than solar and 300 times more than wind. Next slide, please. This is not widely known, but the Everloop through the Everlight project, we learned that we have dispatchability capabilities, and so basically we can act as an earth battery. So going back to what I mentioned earlier, we have to be responsibly operating the wells in order not to cool them off. So we have to ramp up and ramp down on an intraday basis in order to do that reservoir management. But if you look at the top right, you'll see the 24-hour days on the X, 24 hours a day on the X-axis, and the output on the Y, and the solar curve is showing your time of day when basically the sun is shining and all the electrons are going onto the grid. There's a lot of places that baseload is needed, baseload meaning it's always on 24/7. There's a lot of regions, such as California as an example, where you have already a high penetration of variable renewable energy. And when that's the case, you need technologies that can ramp or dispatch. So when the solar is going onto the grid during the day, we can slow the flow rate down and collect heat into the wells. And then when the sun goes down, we can turn the flow rate up and meet or dispatch to that load. But the caveat is we have to ramp it up and down every day. So geothermal, the Everloop, can be a grid hardening technology and pair very well with wind and solar. And when I say grid hardening, it means grids can become unstable if they don't have the right amount of backup generation. So that's when you hear brownouts and blackouts. So the ability to build, as Paul was saying, more geothermal creates that stability that's required. And it actually decreases the cost of your interconnection build as well, because you don't need to overbuild basically solar production or wind production that you may have to curtail. So next slide, please. I don't think I have enough time to go through this, but I wanted to put it in because I know it will go into the library. We did drill this well in New Mexico. We developed some new technology, and that has some implications for all geothermal. If we can, as Greg was saying, repurpose or be able to use the drilling technologies that are out there to geosteer wells, You need to keep your electronics cool, and there's a lot of things you need to do in order to take oil and gas and put it into the hot environment. And that's one of the things we invented here, was the ability to keep the electronics cool. Next slide. This is my last slide. So our first commercial project is in Bavaria. You can see the power plant is almost built. This picture is about 4 years old, or sorry, 4 months old. We're almost 100% built now on the power plant. And the total project here is an 8 megawatt electric project, offsetting 44,000 tons of CO2 per year. We will have power on grid in 2025. I will say that a little known fact about this project is it's not actually, it's going to be a combined heat and power project. So Garrett's Reed, which is a town nearby, is building their district heating infrastructure. And then we will convert this to a combined heat and power so we can supply energy to the grid, but we can also heat the local town. And I just have a summary slide here. So the advanced closed loop systems, they're scalable energy solutions like wind and solar, they're predictable, will create jobs and economic growth. This made in America supply chain is really, really important. The steel, cement, the rigs, the people, the technology transfer, it's all here. And of course, the ability to be 24/7 clean, firm heat and power and to dispatch are very sought after attributes right now in the energy stack. And yeah, that's it for me. And thanks again for inviting me.
Thank you very much, Janine, just for giving us this different perspective on how we can utilize geothermal energy. So we're going to move a little bit, or not a little bit, we're going to switch from electricity generation to look at other uses or ways in which we can harness geothermal energy. I would like to invite Jeff Tester to speak on direct use. Jeff is a professor of sustainable energy systems at Cornell University. So Jeff, the floor is yours. Thank you. And Jeff, you're on mute.
My fault. How about now? Better?
I can hear you now.
Okay, sorry about that. Thanks to the academies and to you, Rita, and the other organizers of this to invite me to make a presentation. I'm actually going to shift gears here a lot. You've heard a lot about the technology for producing electricity and in some cases combined heat and power. I'm going to try and make a case for why we might really need to look at heat more directly, particularly if the United States is going to get to a low carbon footprint overall. So let's try the first slide here if we can. And I hope most of you know that if you live anywhere in the Northern Tier, certainly if you live where we do, or in New England, you realize that heating is a big deal and it takes up a significant amount of fossil fuel combustion. So let's take a look at this. You can go to the next one and the next one. Okay, just hold off for a minute here. So you can either look at this in heating climate zones or you can look at it in heating degree days. And as you go across this northern tier, the areas that are in red or in white obviously have huge number of degree heating days. In fact, in Ithaca, which in upper New York State, and in many of those red areas that you see, you will have actually more heating degree days than they have in Reykjavik, Iceland. So it's a big load. It's not always uniformly distributed over the course of the year. So capacity factor throughout the year is going to be important too. But in terms of the actual energy consumed, it's a significant amount. So we looked at this. Go to the next piece here, please. Thank you. So how much of an opportunity might this be for district heating and carbon neutral district heating in the northern tier? So let's look at the next slide. So this compares just the amount of low temperature heat demand. This is below, say, a temperature of about 100 or 120 degrees centigrade with the electricity consumption in those areas. So looking at New England and across that northern tier, as these colors get darker and darker, the heating demand is a significant portion of the total energy consumption, but greater proportion than it is in terms of electricity. And if we looked at carbon footprint, we'd see a similar graph. So I'm seeing some notes come up here, but I'm assuming that doesn't matter right now. you would see a similar graph where the carbon footprint, depending on how that particular state produces its electricity, would also be significantly higher in states that have a large heating demand. So let's look at the next slide. So this was a study we did several years ago because we were kind of curious about where energy comes from, how much of it is used in terms of the kind of total amount of primary energy consumed per year in the US. So to get to a very large unit, we consume as a country about 100 exajoules. That's 10 to the 18th joules if you like those units, or if you wanted to put it in BTUs, it would be 10 to the 15th 100 quads or 10 to the 15th BTUs. But so the scale on the bottom axis is in temperatures, and the scale on the vertical axis tells you how much in terms of these exajoules are consumed for different end uses. So at below, let's say 100 degrees centigrade, the boiling point of water, you can see that about 20% of US energy use comes from burning, basically, mostly natural gas in this country and oil, and in some cases propane. Some of it might come indirectly from the electricity that's produced, but since we have such a large fraction of our electric footprint coming from natural gas as well, that also contributes to a combustion-based commitment to that 20% of US energy use. So if you were to ask the question a little bit differently, not that electricity isn't important, it's incredibly important for the country, but if we really wanted to get to low carbon, we would have to address heating as well. Some of that can come naturally for geothermal because of the nature of its resource, but it turns out that we're burning fossil fuels when we put them in a furnace at maybe 1,000 or 2,000 degrees centigrade, and then we're immediately degrading the quality of that heat from a thermodynamic point of view, even from an economic point of view, down to low temperatures for providing hot water or space heating. So what could we do to change this? So let's go to the next slide. So if you, again, try to take a national look here at what the decarbonization goals are, roughly now there are about 16 states that have incredibly aggressive goals to decarbonize their energy use. And this will have to go beyond just electricity. It would obviously have to cover transportation. That sector could require and will require a lot more electricity for sure, but it's still going to be burning high density liquid fuels for a long time. So the other part is in the heating side. And if you look at that carbon footprint across the country, 20 to 40% of that, every state's carbon footprint is coming from heating in that northern tier. So what we would obviously need is a scalable and affordable, sustainable, low carbon option that we could do heating with. So geothermal in many ways is a perfect fit for that. In the next talk, you're going to hear about heat pumps. That's one way to do it. They still require a lot of electricity, so you're not getting rid of that. This kind of coefficient of performance that is thrown around a lot today is going to tell us a lot about how much heating we can do per unit of electricity that we're utilizing. And if we go to direct use, that coefficient of performance is very high. It's also higher for geothermal heat pumps, but the efficiency of converting low temperature heat into electricity, as Rita pointed out and others, is a big challenge thermodynamically. I mean, roughly speaking, you might get 10% of it back, but in direct use, you could maybe get 90% of it actually utilized, and you don't have to go to really high temperatures. So let's look at the next slide. This gives you an idea. If you were going to drill, in this case, to 4.5 kilometers, we get a similar picture of the country if we went to a shallower depth, say 3 kilometers, maybe 10,000 feet or so. And if you look at the western part of the country, it shouldn't be any surprise that this is the area where we have pretty high grade geothermal resources, very high gradients, much higher heat flow, and it's easier to reach higher temperatures, which would be attractive, certainly more attractive for converting that thermal energy into electricity. But if we're going to look at the eastern side of the country, you can see that highlighted region from New York through Pennsylvania, West Virginia, that's the Appalachian Basin. There's a lot of drilling that's gone on in that area over many years. So there's a lot of very good data in terms of bottom hole temperatures and a reliable source of what that temperature might be at a given depth. But you're not going to get uniformly in that eastern part of the country to very high temperatures unless you're willing to go incredibly deep. And that will be more expensive. And you have many other ways in which you're, dealing with the decarbonization of that sector. So it might be important to kind of concentrate on the heating side of this. So let's go to the next slide. So just to show you that you can do things, obviously, in the eastern part of the country, almost all the electricity development in the US is in a few western states, California, Nevada, and a few others. And there's virtually nothing in the eastern side of the country right now, other than heat pumps, of course, and there's a lot of those. But those are dealing with very shallow resources. So we, with the support of the Department of Energy and Cornell's own support, we decided that we had to move towards looking at this option for the campus. So an exploratory well was drilled in 2022 over a 2-month period to 3 kilometers. It's a pretty much a vertical well here to try and tell us about the lithology, the temperatures that are there, and what the permeability of different zones might be. But ultimately, let's look at the next slide. This would fit into an energy system where the campus itself, which does have a district heating loop and also provides all the electricity right now with a pretty efficient natural gas-fired combined heat and cycle plant, would have to be replaced with something that represents carbon neutral electricity and carbon neutral heating. So the thought is that we would take what Cornell's demand is for heating in the wintertime on sort of a base load is about 50 megawatts of thermal energy. On a really cold day, of which we have 20 or so per year in this particular region, we might go to 90 or 100 megawatts. So you have to kind of blend dealing with the sort of uniform base load heating capacity, which we feel could come from a deep geothermal system, perhaps at 10,000 feet, with what we'll call an EGS reservoir. Cornell's given it a slightly different name. We're calling it earth source heat. And it would involve a set of laterals and with a similar kind of design to what you heard about the Fervo system, but it would not be trying to produce electricity. So that changes the demand on what the performance would have to be in terms of cost. And so instead of looking at a levelized cost of electricity, we'd be looking at a levelized cost of heat. Combined with that, there would be some sort of peaking capability. And it turns out we have a lot of waste biomass on a campus of this size. We also have cows, which produce a fair amount of manure. And so the combination of those two biomass sources might be ideal for filling in that peak heating load, which only represents a few percent of the total demand. But when you need it, you really need it when you get to 90 or 100 megawatts. The other aspect of this is to use centralized heat pumps, high efficiency heat pumps, and thermal storage to sort of level the demand that you're going to need cyclically throughout the year or day to day. And this is a concept that has been used quite effectively. A good example of this would be in the Paris Basin project, where they have a limited amount of temperature they can get out of an aquifer, and they can enhance that with pretty high coefficient of performance heat pumps to really make the system economic. So let's go to the next slide. There's only 2 slides left. This one talks about what some of the opportunities might be for direct use. So there's a huge thermal energy demand at low temperatures in the US and in many other countries. Next. We have a lot of widely distributed resources, particularly in this range of 3 to 4 kilometers, which is certainly accessible with today's technology. And the cost of drilling, as you've heard from the other presentations, is coming down. That obviously helps direct use as well as electricity production. Next. In terms of utilization or thermal efficiency, when you look at a thermal efficiency of converting relatively low temperature heat from a geothermal system into electricity, you're dealing with probably this 10 to 15% at best thermal efficiency. Whereas if we're using the heat directly, you could certainly talk about 80 to 90% plus or so. So it is a little different than capacity factor here. We're talking about making as much use of that enthalpy we're paying for to get out of the ground and turning it into a marketable product, which would be the equivalent of levelized cost of heat versus levelized cost of electricity. Next. The economics, therefore, are a lot better when we talk about heat versus electricity. And if you look at New York, for an example, and you'll have these mixed units here, I apologize for that, but if we look at the cost of natural gas delivered to a house right now or delivered to a residence, it's about $15 a million BTUs. And if we look at the levelized cost of electricity, at least at the residential level, it's about 15 to 16 cents per kilowatt hour. On an equivalent basis, this changes the way in which you'd have to produce a geothermal system. It relaxes the amount of flow that you have to have in the system. You could have more wells, therefore producing less flow per well. That's a big incentive for lowering the levelized cost of heat. And you have to look at this obviously in the context of what you have in a given site. But looking at what we have, which is temperatures of about 80 to 90 degrees centigrade at 10,000 feet or 3 kilometers, the levelized cost of heat in our calculations, based on reasonable assumptions about what the productivity would be, is about $5 to $6 per million BTUs, as compared to what I was talking about, the $15 or so. Even if you went to commercial rates, that would only drop to about $9 or $10 or so. And so it looks very attractive from an investment point of view, particularly if you're a college campus or a university campus, and you're not necessarily trying to make a profit, but you're trying to avoid the cost of having to purchase essentially a high carbon footprint energy. Let's go to the next one. And so that's the scalable option that we hope would see a lot more interest and use in this part of the country. I think there's a next slide talks about some of the challenges. Okay, so it wouldn't be fair to say you need infrastructure. You heard this in the previous presentation. That requires a huge investment. Some places have this already, but in the United States, it's pretty limited. Certainly large universities, certain urban district heating systems exist for sure, but we would have to expand this tremendously if we were going to actually take advantage of this. So it would be a different kind of investment. It could be a private investment on the side of the development of the subsurface, but a public investment on the side of the infrastructure needed to connect it to a district heating system. The next challenge, you're going to have to do multiple demonstrations. As much as we'd like to think that doing one at a particular site in the eastern part of the country might be enough, I think the recommendations that we've heard from many of our other previous examinations of studies like this is you're going to have to commit yourself to look at a lot of different geologies and a lot of different situations with respect to demand in order to really validate the reservoir performance that's needed for these systems. The next is that certainly these heating dominated regions, so it's not just one or two states, it goes across a big sector of the United States where you could develop direct use, assuming you could have the infrastructure in place. And next, you have to have a certain size to make this work. So it's very different than what you might consider for a ground source or geothermal heat pump, or even a collection of those for a small housing community or something like that. You're really going to have a lot of people connected to this in order to make it economic, because of the scale of the natural scale of a direct use system. And finally, extensive retrofitting to hot water systems for buildings that already exist are going to have to be done. If you have a hot air system or a higher temperature system, you're going to have to go to something that would deal with hot water. So that is expensive. And we can't build all just new buildings. So to do that, you're going to have a hot water distribution system, probably larger radiators. Certain countries have done this. And then finally, a lot of public education and outreach is going to be needed to address the concerns for requiring water use, the potential for induced seismicity and other things, because we're in a big portion of the country, particularly the eastern part of the country, where it's not federal land and it's not state land, it's primarily private land. So that changes the regulatory environment, changes the kind of outreach you'd have to do, and they're pretty densely populated as well. So I'd like to end here and turn it back over to you, Rita. Thank you very much.
Thank you, Jeff. Thank you very much for giving us this different perspective on how we could use geothermal energy. So I'm going to invite Tara. Okay, so our next presentation is on super hot rock. We'll hear from Tara Rogers. Tara is the program director for super hot rock energy at the Clean Air Task Force. So Tara, you're welcome.
Thank you, Rita. And please advance the slide. Clean Air Task Force, just briefly on why Clean Air Task Force, an environmental nonprofit, is leaning into this space. We choose our technologies based on our belief that it could be transformative in efforts to decarbonize the energy sector. So this is very much a focus on power and the concentrated outputs and from emissions that come from power producers. In our white space analysis, geothermal has a lot of very unique characteristics that I trust Rita covered in her first section here. But if you could please advance the slide. We have chosen to focus on ultra deep or specifically ultra high temperature geothermal. In this particular slide, please don't interpret this as being a focus on EGS versus closed loop. This caricature is just actually intended to draw your attention to the, we'll call it the colloquial, what has been conventional geothermal systems looking for those natural pockets of hot water, then moving into what is happening today, the temperatures accessible today, and the next generation techniques, both covered in the EGS and the closed loop systems, but often top out at temperatures that have been defined by other industries. So specifically using techniques from the oil and gas industry, the temperatures in which they needed to operate tended to top out at 200 Celsius. And so that is the activity that we are seeing today. It is our hypothesis that by pushing to higher temperature formations, this is higher enthalpy systems, we will inherently drive to a more cost competitive product. And while that may not be necessary in certain markets, as we look to the growing regions of the world, the developing economies, the areas where we have no expectation for a subsidized carbon market, we believe that driving to the lowest possible LCOE is the best path to creating the largest market and the most impact when it comes to climate. So we are focusing primarily from a technology focus into the ultra high temperature formations and how do we unlock those. If you could please advance the slide. So what has made this possible? I think, oftentimes I get this question, geothermal has been around for literally 100 years. Why haven't we done this yet? What has changed to make it possible now? And the short answer is these two major ingredients. One is that we saw the immense learnings that happened in the shale revolution in the mid-2010s and can now expect to replicate them in the same drilling practices that we are using both in the US West and globally. So that's one. Some of those technologies include hydraulic fracturing and horizontal drilling, as well as some casing completion techniques. That, when you add it on to some of the research that came from investments mainly out of Horizon 2020, which was a European allocation of funding to understand ultra high temperature resources, what we saw, namely, I think the best example in this case is IDDP2, where what was an average output of between 5-8 megawatts per well in that region jumped to 38 in just one well. So demonstrating that the ultra high enthalpy systems of the ability to drive higher and higher temperatures reduces the total cost by increasing the output. So as you can see, Lazard might turn over if they saw the way that we altered their diagram here to the right. But ultimately, the goal is the lowest cost electrons so that we can be certain that the growing areas of the world that need to satisfy energy demand will opt for a cleaner source of electricity. Please go ahead. So in this space, why do we believe that the LCOE is so dramatically affected by this target of both the dry rock conditions and ultra high temperature that is defined at 400 Celsius and higher? So the first is by focusing on that dry rock condition. This is to say we're no longer confined to the unique areas of the globe where these pockets of hot water naturally exist. We can do two things. One is we can mitigate the risks of dry holes. In fact, actually, that is the point. And in doing so, we can standardize the way that the well is executed. So the intense subsurface expertise necessary to track those pockets of hot water are no longer necessary, and ultimately reduces the cost of capital by removing that risk factor. The second is in shooting for these dry rock conditions, this more ubiquitous approach to the subsurface, we make it possible in more areas of the world, therein driving up both supply and demand, and ultimately increasing the standardization of all of the equipment, both in the subsurface and in the surface. And this is a phenomenon we've seen across the energy market. Let's using, for example, solar. As we saw manufacturing increase, we saw the cost decrease. And so we very much expect that by moving into a broader spectrum of dry rock conditions possible anywhere, we will ultimately see a reduction in cost due to standardization. Next slide. The other lever here is that targeting ultra high temperature formations. Now, in doing these ultra high temperature formations, we can, and now in our mind's eye, start to imagine projects that are competitive in size with some of our other very dense land footprint locations, such as nuclear outputs and coal outputs. When we did our original modeling of nth of kind, we ended up choosing turbines of approximately 250 megawatts, as we found that that was the common off-the-shelf size that we saw in the classic conventional fossil fuel network, and expect that there's no reason that we can't also replicate that in a geothermal field where each well is producing anywhere between 35 and 50 megawatts, ultimately reducing the balance of plant. This is also important when you look at the capital stack, because the capital stack indicates that at its nth of kind size, nearly half the cost of the project still sits in the surface equipment. So continually pushing toward reducing the cost of that equipment will show up in the LCOA. Second item here, I think is quite easy to wrap your head around. If one well now produces between 35 and 50 megawatts, we no longer need the same number of wells. So reducing the footprint, of course, but also lowering the total cost by lowering the number of wells. And finally, I know there's been quite a bit of commentary on this. The idea of increasing the enthalpy in your working fluid will inherently increase the efficiency of your surface equipment. Right now, we see on average a 7 to 14% conversion at the surface in these lower temperatures. It is our expectation that we will start to see something between 20 and 24% efficiency once we begin to standardize on this higher enthalpy steam or fluid flow at the surface. Go ahead. And here, I think the proof is that this is happening already. We're seeing this mainly in drilling right now, but we're also seeing a continual reduction in price. And in relation to some of the other competitors in clean firm, we believe geothermal is empowered to continue to drive down that price really long into the future. Next slide. Now, this is the painful part. So I do spend a good nearly 50% of my time focusing on how policy and public funding can help us accomplish these goals. And despite the unparalleled climate impact, and I'll say that differently, despite the unparalleled market impact of geothermal, we are seeing, we'll just call it a pittance of policy and public funding go toward this technology. We do hope that through seminars like this and focus and additional research will continue to raise awareness around the incredible impact this can have, and hope that it shows up in our ability to invest both in research and development toward tools that make ultra-high temperatures possible, but also in demonstrations and further development and investments in the transmission. Next. So I think that we have covered 90% of this. I do want to point out there that we, despite showing that very doom and gloom pittance of geothermal investment that has happened thus far, we are seeing growing policy momentum in key regions and in key states. So I don't want to end this in the expectation that we aren't seeing. I have heard many times in the last couple of years, we're entering a decade of geothermal, and I do believe that is the case. And finally, one of the more exciting parts of this is as of approximately a month ago, we now have 3 unique projects in progress, exploring super hot rock in dry rock conditions. They are with companies that have credibility in operating at these temperatures for 20+ years, and the belief that this is going to be a big part of our energy portfolio going forward. Go ahead, Brian. There's just one more here. I pull this graph frequently. It is often used within the context of climate, and all of our best efforts thus far have only created this small ribbon of green. And that this is not a geothermal comment. This is just solar, wind, renewables, anything that is considered low to zero carbon options. And despite our best efforts, this is what we are seeing. Please click forward one more. And with the market is not going down, the market is not plateauing, the market is increasing. And so the idea of the size of this market and the ability to impact the size of this, of both the climate and the energy system, is truly unparalleled. I hope very much that these that our presentations today help drive more questions and help fill that gap. Thank you, Rita. I think that's it. Thank you for inviting me today.
Oh, thank you very much, Tara. Thank you. Really love hearing about super hot rock. Okay, so I'm going to move to our last talk before we start the panel session, and it's going to be on heating and cooling. We will hear from Kathy Hannon. Kathy is the founder and president at Dandelion. So Kathy, over to you, please.
Thank you, Rita. And Jeff, I appreciated your presentation as giving a very nice setup to why moving thermal energy, especially in cold climates, over to renewables will be so important for decarbonizing our energy use in the United States. Next slide. So I'm going to continue on that theme. Dandelion I co-founded the company in 2017. Our mission is to make it simple and cost-effective for homeowners and home builders to use geothermal heat pumps instead of what they would use otherwise, which is typically a gas or fuel oil furnace and air conditioning, or an air source heat pump increasingly. So our installations are much simpler than most of what has been discussed in this presentation to date. We're only going 300 to 500 feet deep. That's a typical depth of a residential geothermal borehole. A typical house will have 1 borehole, maybe 2. And geothermal is a great product. It's twice as efficient, more than twice as efficient as air source in cold climates, and much more efficient than a typical furnace or boiler. And you don't need a backup system even when it's really cold out. So you can go fully electric. Next slide, please. And so I'm going to talk about sort of some of the things Dandelion has done in our quest to bring down the cost and make these systems simpler and more scalable. And much of this stuff might strike you as fairly simple, which I think it is arguably, but it's been a lot of simple advances that really add up for a cumulative, very significant reduction in cost and complexity. So to get us started, one of the things that we did from the beginning was, the ground loop, as for all types of geothermal systems, is a cost driver of the total cost, a major cost driver. And so putting in the right amount of ground loop is a key basic thing to do to make sure you're not undersizing the ground loop, in which case you would not get enough heating or cooling. But you don't want to oversize it and then pay a lot more than you need to pay for the ground loop. So in our industry of geothermal heat pump installation, it's for residential, most practitioners are using rules of thumb. They're not using geological data or equations or math to size these ground loops. Most people are just using rules of thumb. And this results in a ground loop that can be as much as twice as big as it needs to be. So one of the things that we've done is just use thermal conductivity data and deep earth temperature data and standard loop sizing equations to make sure that the ground loop is sized correctly for the home that it's going to serve. And this alone has decreased the size of the ground loop by about 40% on average. So again, I know it's foundational, but it is still a change in our industry that we're working to standardize across the industry. Next slide, please. In addition to putting in the right size ground loop, one of the big obstacles that we encountered at the beginning of our work was a lot of the rigs that were used in residential to put those boreholes in that are 300 to 500 feet deep were water well rigs. And I should mention Dandelion standardizes around closed loop systems. We do closed loop vertical systems. And the reason for that is cost reduction. It requires standardization. And you can always put a closed loop, almost always, I should say, put a closed loop vertical bore next to a house. Most homes don't have room for horizontal. You just need more land than most homes have to do horizontal loops. And open loop systems require a certain amount of water resource available, which is not always there. And there are many more regulations. So we do closed loop vertical. The wells that were available to us at the beginning of the company were water well rigs, and they were too big to fit in half of the homeowners' yards that wanted geothermal. So the beginning of the company, we sold systems directly to homeowners. We still do that, though more of our business over time has become working with home builders. And our homeowners are mostly in Massachusetts, Connecticut, and New York. This picture shows you the yard of a homeowner in Massachusetts that we installed last August. And you can see that we have a smaller rig. It's a Kamakio rig used for this type of work in Sweden, but it hadn't been used in the US. You can see it's connected to a little dumpster that's collecting all the water and mud and spoils coming out of the hole, so it's not going all over the homeowner's yard. You can see how clean the site looks. And then that compressor is sitting at the top of the picture, and you can see how the fact that the compressor is not mounted to the rig gives us the flexibility to sort of arrange these pieces so that they fit nicely right next to that home. And if you look at the chimney on the roof of the home, it gives you a sense of where that furnace likely sits. And you can see we're drilling very close to that so that the trench going into the house can be very small and therefore inexpensive. So this suite of equipment is optimized for residential geothermal. It makes it much easier to serve most homes, and then a much better customer experience because we're keeping the site clean and drilling in the most optimal place. Next slide, please. When I got started with Dandelion, I did not know that there would be so much work to do on the inside of the home too, to make geothermal a more practical option for people, but there really has been a lot of work that's been required. And that's mostly because a lot of homes that exist today in the United States were not built for heat pumps, they were built for furnaces, and that just causes some problems. So over time, we actually built a geothermal heat pump that is specifically optimized for cold climate retrofit. And it simplified our installation process quite a bit and made it more cost effective. Next slide, please. The reason that it's difficult, well, one major reason I should say, that it's difficult to retrofit a home that was designed to work with a furnace, especially in a cold climate, with a heat pump, and this could be either air source or ground source, is that heat pumps generally produce air around 95 to 100 degrees Fahrenheit, whereas furnaces are often producing air that's over 120 degrees Fahrenheit. And when you have warmer air, you don't need as much of it to provide a given amount of heat to a space. And so the ductwork that's been built into many of our houses in the United States, it's too small to handle the airflow that a heat pump requires. And changing and retrofitting ductwork is a very, it's very expensive, it's very invasive, and often the need to do so will price a retrofit out of reach for the homeowner. So in our heat pump design, we designed it so that it's able to produce air that's up to 100 degrees Fahrenheit, so that in homes that have ductwork that's undersized for a typical heat pump, we can just, work with the ductwork that's there. And this saves the homeowner a tremendous amount of cost and complexity. Next slide, please. This this heat pump design also is designed for shorter ground loops. So the way that the geothermal heat pump industry is standardized today is that geothermal heat pumps have been built to handle water as cold as 30 degrees. So the way you size the ground loop and figure out how long it needs to be for a given house is you're solving an equation that asks, how long does this ground loop have to be in order so that the water going through it never gets colder than 30 degrees, even in, the end of January on the coldest day. 30 degrees is fairly arbitrary. It's just heat pump manufacturers have designed their heat pumps to accept 30-degree water minimum. So we designed ground loops to provide that water. We decided, let's design a heat pump that works with 25-degree incoming water and is optimized for that. And the amount of heat our heat pump produces with 25-degree entering water is actually more than what other geothermal heat pumps produce at 30 degrees. So we're able to extract more heat from colder water. That might seem like a small difference, 25 degrees, 30 degrees, but it actually it decreases the required ground loop length by 20%. So it is significant. Next slide, please. We also wanted, another obstacle we face is that sometimes when you convert a home from using a furnace to a heat pump of any type, you're required to upgrade the main panel sometimes, not always, but sometimes, because you're going from a non-electric heating solution to an electric heating solution, and not all homes have the infrastructure to make that possible. And these main panel upgrades, again, very expensive and add complexity to the job. They can take months, and you have to coordinate with utility, and they can cost between $4,000 and $9,000. So we designed our unit to require about half the amperage from the main panel that a typical heat pump would require, to really minimize the need to do this type of main panel upgrade, saving homeowners a lot of cost and making the installation happen much more quickly. Next slide, please. So that's just a few examples of some of the things that we've done to try to innovate in products that are available in the geothermal heat pump market to make it possible for our homeowners just to decide they're ready to fully electrify their homes and choose geothermal, because with all the incentives available, the federal tax credit, a lot of utility rebates, it's actually, in many cases, the least expensive way for them to do that. Thank you.
Thank you. Thank you very much, Kathy. And thank you to all our presenters. So we do have some time for questions and answers, both from the audience and committee members and agency representatives, you're welcome to raise your hand on Zoom and I will call on you. And I'm going to start with a general question for all the panelists, okay? Maybe I'll call, yeah. So I think the first one I have for everyone is, are there any gaps in funding opportunities for research and development in all of the areas you've talked about? And if so, what's the highest priority for you? Like, what would that priority be for investment in R&D? Kathy, let me start with you. And
Sure.
yeah, okay.
Yeah.
Yeah.
Yeah, our challenge has always been that in the past, I would say that most geothermal grants specify geothermal electricity, which we don't qualify for, and most heat pump grants specify air source heat pumps, which we don't qualify for. So we're in this no man's land where we really don't have a lot of grants that we qualify for. We would really benefit from them. There's a lot of R&D potential. Like you can see from the type of innovations that I illustrated how much low-hanging fruit there still is, I guess, to make geothermal more cost-effective and widely available. But I appreciate even being part of this conversation because I think typically, yeah, we see the geothermal camp and the air source heat pump camp, and we're not included in either most of the time.
Not fun to be sitting somewhere on the fence, right? Jeff, if you could share with us what you think.
So aside from these important things that Kathy's pointing out and what you're probably going to hear, the other D in my area is deployment too, and demonstration. Those two Ds, they require significant investments. But I want to back up a little bit to get to the innovation that we've seen with the talks this morning, both with closed loop systems and what Fervo has been able to do with these long laterals. Regardless of what we're talking about, we still have to have thermal access to a lot of volume of rock, one way or the other. And that requires certainly knowledge about how water or heat is being conducted. In the case of closed loop, maybe by conduction dominantly, although you could have some convection. But in the open fracture system, in spite of how many fractures you might have and what their width might be in terms of a well separation distance, the flow across those fractures is critical. And being able to control that flow, whether it's a natural system or an EGS system or anything else, is going to be important. That goes away, obviously, with a closed loop system, but it has other challenges, as Jeannie's pointed out, too. But I think that's an area where more investment could come in research. We see a lot in stimulation technology and drilling technology, but not so much in the diagnostics and control of flow and the thermal history of a geothermal system. And we sort of learn this the hard way when we get rapid drawdown in a natural system. We have to drill more wells. But being able to extend the life and to take the most advantage of that rock mass that's in place that we have obviously access to, but we need thermal access to it as well. So that to me is a real area where there could be more investment for research. And it's definitely subsurface science and engineering for sure.
Yeah.
So I'll stop there.
Yeah, Greg, I know he's touching on some things. EGS, what do you think?
Yeah, so I really like to build on Jeff's comments. Deployment of new ideas and new technologies in the field is really what allowed oil and gas to make its dramatic impact in the unconventional space. So I'm a big proponent of that. Jeff talked about the fluid flow between the injectors and the producers. Putting monitor wells between the injectors and producers and being able to see using things like fiber optics or other measurement devices how that thermal front is moving. It's going to be absolutely crucial for understanding how we build the wells, how we operate the wells. So there's a lot of opportunity in this space. Really happy that people like Joe Moore and John McLennan at Utah Forge are already talking about this. Tara's trying to push a lot of things on the super hot rock side. At the end of the day, you got to get wells in the ground, testing new concepts, new technologies if you're going to make progress.
Yeah. Janine, do you want to say something too on the R&D side?
Sure, I can make it quick. A lot of it's been covered, but we didn't talk much about geomechanics. There's a lot of work needed in geomechanics, especially for deep drilling. And there's not a lot of availability for high temperature, high pressure lab equipment. There's no real coring tools. There's work we need to do for all of our sort of oil and gas bottom hole assemblies and bits and things to transfer into these really high temperature environments. So I think you know, the DOE's done a really great job with Forge in terms of pushing boundaries there, but there's still much more to be done, especially as we drill deeper into the brittle ductile transition zone.
So speaking of high temperature terra, yeah, what would you say?
Yeah, thank you, Rita. Over the last 12 months, my team and I have been focusing on a report series. It's 5 parts. The question at hand, each one is answering, is what can't we do in a technical sense that is keeping us from routinely executing projects in this brittle ductile transition at ultra high temperatures. What we found is, of course, material science is known in other industries, but not executed in this particular one in the field specifically. So few of the technology or R&D opportunities that I see sort of very front and center is alloy research, coating research that can help both insulate and strengthen, especially during thermal flux. I think it's important to recognize that it is not in a continuous operation at presumably 400, but that it should be capable of going up and down plus or minus 300 to 400 degrees during any given week's operation. I think the good news is, however, that this Bridging the Gap series and conversations around some of these technical gaps have not gone unheard. We are seeing interest from ARPA-E, who has submitted an RFI on this particular topic, and there is continual discussion also in Congress. We're seeing a particular bill pass or be considered at the House this week around ultra high temperature material science and research. That also includes, going back to Greg and Jeff's comments, around demonstrations. Unlike the solar industry, for example, you can't take your bench scale solution and test it without actually doing it at depth. And that makes R&D very difficult to get it past that TRL threshold that triggers public funding. So part of the importance of this conversation is to understand that the way that public funding is triggered by technology readiness level expectations is that we have to do it in the field, and in the field is often 2 miles deep. And so that is an important part of that sort of understanding on how we progress technologies, especially these techs that have the ability to be so impactful on a market level.
Yeah, so Paul, people might say that, you know, conventional geothermal has been there for a long while, but are there any gaps that would require funding opportunities or R&D? Okay, let's see. Okay, we don't have Paul now. Okay, so I'll go to Doug. We see your hand raised if you want to ask your question.
Yeah, I've actually got 2 questions. The technical one first. I'd be interested in thoughts on how you think we're going to be surprised at the brittle ductile transition. In other words, the assumptions that we're going in with versus the way that that's actually going to manifest itself as you start moving deeper. That's one. But the other one goes back to a little bit to what everybody has sort of referenced. We've seen a lot of advances that came out of the Forge test site, and Forge took about 5 years of funding to eventually get it to where it could launch. The question is, do you think a dedicated test site for your respective technologies would be beneficial? What would it look like? What would it cost? That's it.
So who would like to take a stab at answering that one?
Tara should go first on the brittle to ductile transition. Nice simple question for you, Tara.
Thank you. Yeah.
Right.
So Doug, as I think about some of the complications we anticipate in the brittle ductile transition, one of the most common ones is concerns around fractures healing and closing. So any efforts made to actually create the flow and matrix in the direct contact, so this is in the EGS model, will those fractures maintain? Good news is just recently some work out of EPNL in Switzerland put out some interesting bench scale analyses and modeled that indicate that they don't expect healing in the context that was previously assumed. That's just in the mechanical sense. However, I'd like to go back to that gap question earlier. What we are very poor at modeling right now is geochemistry expectations in these higher temperature zones, where we're actually precipitating out what might be in the rock and how it will change the permeability in the rock. One way, it truly is on a spectrum. I can't say it necessarily is a concern, and maybe it could improve it, but the modeling there is very poorly understood at these ultra high temperatures. And I'd love to see more work. For example, there are some laboratories in New Zealand that focus on flow reactors at 600 degrees and replicating multiple flows. That is an area that I would love to see the US also lean into to better model so that we can replicate that. That is one of the biggest concerns. I understand, within the horizontal drilling and concerns around, for example, executing closed loop technologies. I think Janine is significantly more abreast on some of any specific technology gaps expected in the brittle duct transition for closed loop. So Janine, I'm throwing you under the bus.
Yeah, no, that's fine. From the closed loop perspective, and we did see that supercritical bill get passed today. There was some interesting language in there about closed, it's really good bill. We're very supportive of it, but I think there's a general lack of understanding of whether or not closed loop is actually technically and practically feasible, which we think it is. But I think when it comes to the geomechanical question in the brittle ductile transition zone, is will your wells creep after you build them, right? Like how ductile is it? So that is the type of research that I think would be, and we submitted that to ARPA-E. We did a whole write-up on that, on what we feel could be researched through the that RFI to help closed loop deployment in brittle ductile become a reality. Cost, as far as the test site, I don't think you need a special test site. I think Forge is a perfectly great test site. I know that there's this idea that we need test sites all around for every, a whole bunch of different geologies across the US, and it is important because, rocks are different. Having said that, we can't really characterize deep down very well. We've already got a site stood up. I think if we want to drill deep, let's drill deep at Forge. I mean, that would be my recommendation. In terms of cost, drilling is expensive. Jeff Tester touched on the RD&D, costs and why it's important. And drilling deep is going to be expensive. And I would say a good starting point is $100 million. One well is going to cost $20 million or more. That's before you put any completion techniques or coring or any geophysical work. So I think there's low dollar R&D we can do, but the real dollars are going to come with putting steel in the ground and drilling deep, and we need a lot of money to do that. Tara, you might have a better answer for cost, but that's mine.
I will say, I think that is a reasonable cost, especially for a couplet, depending on how many you want to do. If the intention is to demonstrate routine drilling over and over, then probably not adequate. But if the intention is to demonstrate flow, it is. I also think that Janine presented a hypothesis that why don't we just drill deeper at Forge? And I think that actually that scratches one itch, which is, can we do this anywhere? Why not there? But there's another sort of perspective, which is perhaps we should do it in a place where we know the heat is really shallow, so that we're not taking risks in well completion at the same time as also executing some of the science necessary to show flow in that subsurface. Both have value, but I do think it is a consideration.
So yeah. Rita, would it be possible also to kind of talk about, I know Janine mentioned this, about different geologies, but super hot is one aspect. And that might be amenable to one site. But when we talk about other regions and the type of geology you have there, we should be at least mentioning deep sedimentary basins are very different than drilling in basement, and kind of the challenges of trying to prove that you can get flow across large extended surface areas has to be done, to me, in repeated geologies in order to prove. If you go back to when we did this report a long time, seems like a long time ago, the Future Geothermal Report, it was pretty clear from the people that were on that panel that no matter what you do, you're going to have to get eventually local in terms of proving a particular resource. So it doesn't mean you can't do certain things at a site like Forge, but you can't do everything. To me, it brings in a bigger group of advocates for geothermal. Solar's put everywhere. We put it in New York State when it's dark here half of the year, and the capacity factor in the wintertime is terrible. It's very different than California. We have to prove that geothermal can be used across this space. And I think heat pumps have done a remarkable job of doing this. They can go in anywhere, basically. You can put them in North Dakota or in Massachusetts or Connecticut, and you know what their performance is going to be. It has other challenges, but we don't have that kind of validation yet, field validation for either EGS or for low temperature geothermal in these other basins. So I think it's a good investment. It's not going to be easy to raise that money, but it's not billions of dollars, but it's certainly more than 100 million for sure. And I think that's both the federal and state governments have to be realistic in what that investment would eventually bring. Whether it's closed loop or open loop or multiple laterals, you still have to go into different geologies eventually. So that's my thought on it, but it doesn't go counter to what Janine's saying. It's just that there's a big space out there, right?
So, Greg, your hand is raised. Is this for a question or comment?
No, it's really to respond to Doug's second question.
Okay.
And I might throw out a slightly different model, which is rather than test sites, which are solely government funded. One of the things we had tremendous success in the oil and gas industry was kind of joint industry operators partnering with the government, partnering with service companies. We did some hydraulic fracturing test sites in the Permian Basin. They delivered wealths of information. They were done quickly, efficiently. I love what Joe and John have done at Utah Forge with their team, but I think there's a chance to kind of distribute the funding, get the operators to put some money in the game. You're seeing that already with some of the projects that have been recently funded by DOE, GTO. Mazama in the super hot rocks, Chevron out in California, Oxy in the DJ Basin. But I think we could do more of that. We could really accelerate progress, make it happen much more quickly, and it can spread the government funding around and also ensure that the knowledge is shared, since if the government funds a project, they always require that the information is put into the public domain.
So Rita, just let me follow on that just quickly, because I think that's an interesting comment, because the geothermal sector has not had consortia like the oil and gas sector has had, like in the deep water Gulf of Mexico or such. So Greg, you feel that you could create $100+ million industry consortia that would be largely funded from the oil and gas sector getting interested in geothermal. Is that sort of a little bit too leading?
I think them totally funding it, I think might be a push right now, because most of the oil and gas companies are just starting into this space, Doug. But I can tell you in the last 6 months, almost every company, every big company in America stood up a geothermal team. Some of them are very public because they've already made investments like Devon's done in Fervo, or the test sites, which are being funded by the US government. But I think there's enough interest now, you can start talking about partnerships and not just the government acting on their own.
Yeah. Thanks, Rita.
All right. Tara, you want to comment or ask a question?
Yeah, actually, it is a follow-on. Always thrilled to hear Greg's experience with the oil and gas sector, especially when it comes to shared data. Doug, I'd actually like to explore this conversation in more of an international perspective. So I do believe, I mentioned earlier, from the super hot lens, we see 3 major players moving forward in 3 very unique regions of the world. We need a platform in which they can share data now, and specifically best practices, where they saw execution work, how do they avoid making the same mistakes twice. And we believe that there are groups already set up like this, like for example, IEA, that could help house this. Now, But taking this to a funding perspective, I also do see there is a possibility of doing this completely private, very similar to what Greg suggested. And the model in which I have in my mind's eye looks a lot like treating the subsurface as we'll call it the equivalent of the wind tunnel, where not every entity, not every major will have their own test bed, but they have access to a test bed and it's shared data for some amount of time. And the surface equipment is a separate matter that is helped to be financed by the major buyers of today. So that could be coalitions of clean energy buyers like SEBA, or it could be unique buyers like we are seeing in the sleeve agreements with Amazon, all of the major data centers. So I do believe there is a chance that it is not a hard no. I think there's a possibility that we could do this in a private market setting, but breaking out the value propositions based on your subsurface, your surface, and your electricity purchase on the back end.
Thank you. Janine, your hand was raised at some point. Was your comment or question addressed already?
I just wanted to make a comment on Greg's comment about these joint industry partnerships. Ever is leading a feasibility study now on behalf of the government of Alberta in partnership with the Canadian Geothermal Energy Association and the Canadian Association of Energy Contractors. That is a mouthful. But what we're looking at is the market viability of a public-private partnership for a technology agnostic drilling testbed accelerator. And we expect to be finished that feasibility study within the next few weeks and hopefully get some good news and approvals from the government to be, and it's open access globally. There has to be some benefits for Alberta in there, but the point is, I can say that we've done robust stakeholder engagement across the oil and gas space, the geothermal space, and the technology space. We have a lot of letters of support, and we do have one or two big oil and gas players looking to be a part of it.
Sounds good. Okay, so there's a question that cuts across a couple of the panelists. It has to do with induced seismicity. This is something that affects public perception as well as it's a technological issue. So Greg, Tara, Jeff, or anyone that wants to address it, what's your take on induced seismicity in the geothermal industry? How are we managing it? How are we addressing it? How are we preventing it? Yeah. Greg, you're mute.
Yeah, sorry. I think there's been an enormous amount of progress made over the last 15 to 20 years on induced seismicity. I mean, it largely has come from the oil and gas industry in that we're drilling tens of thousands of wells a year, hydraulically fracturing them, managing a lot of water, putting a lot of waterway in the ground. And but there's also been lessons from the geothermal space as well. And I would put it into three categories, Rita. One, you want to plan your projects to minimize the chance of induced seismicity. You want to monitor while you're operating. And then finally, you have to have some mitigation options in place. On the minimize side, I mean, we've heard a little bit about this, I think, already in the conversation today, and that you really want to be looking for certain types of geology. And one of the things in the past with EGS was that most people were looking for areas where there was some amount of, or fairly large amount of fracturing and faulting, because they needed to kind of re-stimulate that if you're using vertical wells, with the Basel project in Switzerland being a great example. You want to get completely away from that from an induced seismicity perspective. Peter Meyer gave a great talk out at the Geothermal Rising Conference just a week or so ago about how by moving away from faults, you can really reduce the chance of it ever happening. And actually myself and Mark Zobek, who's a member of the National Academies, is going to be giving a talk at Stanford in February on that same topic. So a lot on the site selection. Then you have to have a monitoring process in place. That's pretty well matured across the oil and gas and geothermal industry at this point. But then once you're monitoring, you have to be able to mitigate against induced seismicity that may be occurring. And there's a number of different lessons learned there. Won't go into all of them here, but I think this is an area where, from a technical perspective, there's been an enormous amount of progress, which should be encouraging for anyone who is concerned about induced seismicity. So I'll leave it with that and let some other people jump in.
Sure, Jeff, you have your hand raised.
So, these are all very important points. But what we have learned, we're in a state that has outlawed gas fracking, New York. Okay, and there's a huge amount of misinformation about induced seismicity associated with that. That's the first problem you have to deal with. And largely, the public, when you talk about stimulation at all, they sort of think that that's going to cause, essentially property damaging or potentially people damaging seismicity. We are in a very aseismic region here in New York. So we've had to be able to guarantee, in a sense, that we're going to protect the public involved with even the drilling of an exploratory well, which has essentially zero probability of any induced seismicity. But going forward, this is going to be a big challenge of public outreach and certainly dealing with the local communities to try and explain the difference between what we're doing in geothermal versus what goes on with deep water, let's say, disposal of frac fluids and things like that, which is an issue. And we don't have that in geothermal. Water is actually our friend, right? Not our enemy here. So I think it's really important to bring the public in at an early stage, particularly in private landowner situations in communities where there's regulators that aren't federal regulators here. They're the local people in the local governments. And we've learned a lot from that and spend a tremendous amount, not money, but a tremendous amount of time trying to make sure that they're on board with the benefits that come out of geothermal as well as the issues that are associated with. So it complements what Greg is saying, but Forge is in a different part of the world from what we're in Ithaca, New York, or what Janine's dealing with in a big city in Europe for sure, or what they had in Basel. So it's kind of a big landscape where you've got to be sure you cover all the local people too, I think. Thank you.
Yeah, okay. So Tara, you want to give a different perspective on that? Yeah.
To point out a few case studies and sort of examples for further research. One specifically, and just to clarify here, the GTO and the DOE does have a pretty clear expectation for projects that receive their funding. It's referred to as the ISMP. So for those that want to look into it more, I think that is, Greg described it quite well in terms of both requiring an upfront risk assessment before, so that is in the siting, and then the monitoring ISMP. And these are practices that we would love to see applied everywhere, because a misstep in this space could be catastrophic for the industry. I also think that it is important, going back to Jeff's comment on community engagement. Another case study is the Eden Project in the UK, where I believe the seismic or what was actually measured was something no greater than in the 2s, yet caused so much unrest and discomfort that the project was paused quite significantly. The hypothesis here, though, is that at no point did it actually get larger than what would have been a passing train. And some community engagement in advance of this may have been able to pacify, we'll call it, some of the sounds and discomforts that did not actually result in really any type of destruction.
Thank you, Tara. Doug, you have a question?
Yeah, I've got a question. It's actually for Jeff and Kathy. It's on the uptake on the low temperature side.
Okay.
So the thermal story that Jeff talked about is compelling. The emission side is compelling. So what are the barriers? Why isn't low temperature, for example, in New England 50 times higher than it is right now?
Jeff, do you want to start, or should I go ahead?
Either way, there's a different landscape. I mean, Kathy, why don't you talk about this? To me, there is a lot of not only interest, but there's a lot of deployment of geothermal heat pumps right now. I mean, tremendous amount. And I think that's a good thing because it's at least in their vocabulary. But talk about, do you really view that as a barrier right now, or is it really something else for you guys?
Yeah, I would say for us, the way that, so just there's different customer groups where the answer will be different. So I'll start just by talking about homeowners. because that's the group I'm most familiar with. And I'm sure, Jeff, you could talk about a different group, but
Sure.
for homeowners, most homeowners, the way they buy HVAC equipment today is you don't think about it, and then something goes wrong, and then you have to solve a problem. And
Right.
if that problem is your heater is broken, that's a pretty urgent problem, especially in the Northeast, or even if your air conditioner is broken, it's uncomfortable. So you optimize for upfront cost and speed, and those things do not favor geothermal today. So I think like most renewable energy technologies, upfront cost for geo is often a little higher. The payback period is very good. Sometimes the upfront cost is actually approaching the same now, which is very exciting, but um, compared to like the cheapest furnace you could get, it will definitely be higher,
Right.
the operating costs will be lower, but you have that issue. But then you also have just like the timeline issue. You need to get permits, which you don't need to get for a furnace. You need to find somebody to install geothermal for you, and very few people do it today. You need to get drilling, and then the ground loops trenched into your house, and then the heat pump installed, and that just takes time. And then because houses haven't been built for heat pumps, it's often not just a simple swap. And so there's just a tremendous amount of complexity. And so the homeowners that we see signing up, and to Jeff's point, I think it is taking off, like it is growing quickly, but the homeowners that we see buying geothermal today, they're proactive replacements. They're people who have decided, I would like to electrify my home. I would like renewable energy. So I'm going to plan ahead and decide to do this. And I'm not going to mind that the installation takes a few months, or that that I might have to take a loan to cover the upfront costs so I can save on the operating cost or whatever it is.
Yeah.
And that's just a small fraction of total homeowners, and not how most people think about it.
Right. I would even add, Kathy, if I could, to what you're saying, because there is interest now in these smaller districts too, where sort of a group of individuals, maybe it's a housing development or something like that, where they actually build it with the idea that there would be a kind of a mini centralized operation for heat pumps. And that seems to make sense too, because it eliminates some of the uncertainty on the part of a homeowner. They're going to be buying essentially the reliability of a hot water system or cool water system, depending on time of year. That seems to be growing in interest too. Would you agree, Kathy, in that area too?
We do see a lot of interest now in thermal energy networks. So these utility scale sort of district systems. And I think part of what's motivating that is natural gas utilities trying to think about the future of their business model once we don't use as much gas. And I do think that's a great solution in certain contexts, but tends to work best when you have a densely built environment, lots of buildings close together with different heating and cooling load patterns, so that there's some efficiency to having it all in a district system. When we work with home builders that are just creating residential neighborhoods, we're seeing a lot of interest there as well. And I think the barrier there is really just it's a change, and a lot of home builders, because of the way their business model works, really value predictability, low risk, like operational simplicity. And so we've been making a lot of progress in demonstrating that it actually is quite simple, and it is actually very low cost, especially in some markets. And I think the point was made that of the value of deployment, and that is certainly true here. I think once we see some major home builders start to move to geothermal, we'll get a lot more following. It's just novel enough, I think, still, that there's this perception of risk, even though in my opinion, it's not very risky.
Right. So let me, if I could move on to the larger challenges ahead, just to give you an example, Doug. If you don't have the infrastructure in place and you really have to do district heating to make it make economically sense, someone has to invest in that. We've evolved in a different way as the United States versus a lot of cities in Europe or other locations. Iceland would be a classic example too. We deliver to homes right now natural gas, water, and electricity. We don't deliver hot water to them, right? And we deliver drinking water. So somebody would have to incentivize that public side of the the long-term infrastructure sort of shift we need to do. It's remarkable to me. We have a sort of an infrastructure emphasis right now, and almost none of it is tied into doing district heating in a larger way. You know, we'll replace bridges and put in some new fiber optics for delivering internet and things like that, but or maybe new water lines or sewage lines and things like that. But we're not necessarily thinking of it in a fully integrated system way. And I think the lack of having a real carbon price or carbon incentive in this country is limiting that right now. I think that would change drastically. You know, if I compare, for instance, air source heat pumps with geothermal heat pumps, a tremendous shift would occur there if they actually looked at the carbon footprint change that occurs because of the higher coefficient of performance of ground source. And that doesn't happen right now. For a builder, the air source unit is cheap. They can just throw in individual things, but the ground source involves a sort of a look at the total cost of ownership, which is the owner of the building as opposed to the builder of the building. And I think that could change with a different way in which mortgages are handled, a different way in which the incentives are there. As Kathy said earlier, that we kind of don't have a level playing field when it comes to incentives, comparing it to photovoltaics or to wind or something like that. And I think that could do a lot for both district heating as well as for heat pumps. To give you one final example, and I'll stop talking here. You know, Cornell, when it tried to look at decarbonization, we looked at a lot of options, Doug, besides just looking at deep geothermal. We looked at small modular nuclear reactors as another way. That would obviously work well for getting rid of carbon and could do district heating at a fairly good scale, certainly at the levels we talked about or we need on a campus of our size. And we also looked at geothermal heat pumps and air source heat pumps. And unfortunately, well, I should say that the realism of a place that has a campus with a 50 megawatt heating load is going to require, in a heating dominated region, is going to require a huge number of wells. Okay. It would make Dandelion happy if we had to come to you and say, we need to drill 10,000 wells now. And you've seen a little bit of an example of this. Ball State would be a good example of what they did there, as you know, Doug, I'm sure. And so it's not a one size fits all here. You want to deal with the rural environments, the individual homeowners, and you want to deal with densely populated areas too. And to me, geothermal can help in all of those areas, unlike some of the other renewables. So it's a beautiful area for the flexibility, I think, and resilience of geothermal to show more capability. I don't know why this hasn't happened faster. You were head of the geothermal division for a while, Doug, so you must have, been frustrated by this too, right? I would think.
Well, to me, there's a through-going theme that binds the low temperature and the super hot and the EGS and the advanced geothermal, which is a need to be thinking long term versus, I mean, Kathy, I think had a really good point that when your heating system goes down, you don't say, I'm going to wait 6 months so I can get the permits. You're just going to replace it. And if you have other energy solutions versus the ones that are actually transformative, it's easier to do doing the near-term ones. So that, to me, that's one of those common threads that basically binds everybody here together.
All right. We could stay and talk all about geothermal all day, but we are running out of time. So I will just give each of the panelists 1 minute or 30 seconds to answer one question, and it has to do with the workforce. So do you see any challenges with workforce demand and supply in your specific areas? And what can we do to overcome these workforce challenges? Okay, and we'll wrap up. And who wants to go first?
I'll go first really quickly. Okay. We have a dying breed of geoscientists across the world. And if you look at any of the presentations today, the front end is always the geoscience. The induced seismicity de-risking is geoscience. So I don't know how I don't have a solution other than we need to tell the story and we need to figure out a way to encourage more people to go into the geoscientists. As far as the transfer for the existing workforce that exists in the oil and gas industry today, the the Pathways to Commercialization Liftoff report did a really good job of showing there's a couple of 100,000 jobs that are transferable. But I don't think that's exactly realistic because we're growing our LNG exports. So like that workforce is kind of spoken for. So there's still some work to be done, and I'll stop there and let someone else give their 2 cents.
I got to just jump on Janine's comment. A lot of what I've been doing the last year is engaging with oil and gas companies and professional society conferences. And I tell you what, there's a lot of really excited people out there when they hear about what's being done in geothermal. I think, we really need to get the message out there that geothermal has changed dramatically in the last few years. The opportunity set is huge. The skill sets that exist in oil and gas are almost all directly transferable. It's not just fracking rocks, it's managing water floods, is thinking about how to drill high temperature wells. There's loads of really important things that can be done to get people excited and then get them moving into this space. So I'm really encouraged by that. I'll leave it at that.
In my world, when we came up with what should the drilling system look like for shallow, it turns out like it's a lot less important what's the rate of penetration or even how deep can it go. What you really want to focus on is how easily is it to train on, how simple is it to operate, and how easy is it to move it from house to house. And so with our current setup, we can train somebody who's not a driller to work our system in 6 months. However, our limiter is licensing. So lots of states have very difficult licensing requirements that actually make it very difficult to get new people into the field. That's actually also true on the inside of the house. Licenses to work with sheet metal or be an electrician or, be a plumber, like a lot of the skill sets that our system requires, it's very hard. It's state by state. It's even more local than that, what's required. So there's a very high soft cost associated, and it does limit workforce.
I'd like to add to Janine's point too about the subsurface. So you don't have to be a geologist or an earth scientist necessarily to work on this problem. I went into this field with no knowledge. I was a chemical engineer, but a lot of the fundamentals of engineering can be I won't say easily, with some effort, can be taken in a collaborative effort, working with earth scientists to really build that workforce. And we need to focus more on that. I'm in the teaching business and have been for a long time. And once you start to talk about with conventional engineers, and they can kind of see what they can do in the subsurface environment, they can use their knowledge of thermodynamics and of fluid flow and heat transfer, and also geomechanics that are used in different systems in a pretty interesting, exciting way. And convincing them that, this is not just about going to an old industry. I'm not trying to take a shot at ConocoPhillips here, but we all have to evolve in certain ways. And it's just a perfect match for the high technology that exists right now in the oil and gas industry to kind of translate it over to more carbon neutral geoscience and geothermal applications. And I see this as a great growth area, but believe me, there's not enough earth scientists right now for sure. We have to work on that. And I think it would apply across the board. Super hot is going to be even more challenging, Tara. You're going to need a lot of people to do this because there are areas where we have little or no data at all. Lots of models and not much data. So I think if I was going into this as a young person, I'd say this is way more exciting than just doing photovoltaics forever or just doing wind turbine technology, because it's got so many opportunities to make a contribution. So I know I'm talking to the choir here, but we need to do that more externally too. And for you, Rita, as a young instructor right now, I'm sure you can see that kind of transition in your own sense.
Definitely.
Thank you.
Yeah, Tara.
I do think there is an underlying, we have not really talked much about the electricity part of this game. And so I will say +1 to everything that has been said here in the subsurface and the opportunity for us to rebrand our subsurface energy academic institutions and opportunities to be greater than the fossil fuel market. And perhaps that will keep that pipeline flowing. But from a policy and even perspective, I think that we have not given adequate time and research to the systems analysis to help us understand grid reliability and consistency. How do we create markets that truly value the firm profiles that our geothermal and nuclear facilities, for example, can continuously produce and satisfy that growing baseload demand? So that applies to both sort of the policy side of how do we make those infrastructure shifts in the way we think, but also in the actual industry side of looking far enough out to understand the effects of intermittent energy supplies on our grid, and how do we continually provide clean and firm at a price that is competitive. So that is that view that I think we should be shifting in the way that we're thinking about electricity and training the people looking at the systems.
All right, thank you all very much. And, Tara, you touched on policy. We will take a break, 10-minute break, and we'll come back and we'll continue with a discussion on policy, economics, and social consideration. Thank you to all our attendees so far and our panelists. Okay.
Thank you all for sticking with us after the break. I thought the first panel was incredibly insightful and interesting, and thanks, Rita, for moderating. We are going to move on to talk about another aspect of geothermal development, which centers more around policy, economic, social, stakeholder considerations of geothermal. I'm Sarah Jewett. I'm the Vice President of Strategy for Fervo Energy. We are a private geothermal energy developer, and we are currently building a 400 megawatt geothermal power project in southwestern Utah. We brought our first project online, which was a 3.5 megawatt project in north central Nevada last year. That was brought online at an existing geothermal power facility. And so the project we're building today is a large scale version of that, and it is intended to produce electricity for the grid. We are also working on direct heat projects and various behind the meter types of developments. So that's what Fervo does. I will be moderating this panel with some really great panelists. And I'm going to introduce them sort of as they come up, the way we did on the last panel. As Margot said, and as Rita said during the last panel, please feel free to gather up your question and answers and send them over, because we'll do a similar format for this panel that we did for last. Each panelist will present, and then we will do a more moderated panel and Q&A at the end. With that said, I'm going to go ahead and introduce our first speaker, who is Michael O'Connor. Mike is a portfolio strategist focused on geothermal energy and CCUS in the Office of Clean Energy for Department of Energy. He is also one of the authors of Department of Energy's Geothermal Liftoff Report, published in March, which is what he will discuss today. So over to you, Mike.
Thank you so much, Sarah. Just making sure you can hear me. Thumbs up if you can hear me. Cool, awesome. Yeah, I'm happy to join this great webinar. It's awesome to have 173 people on to talk about this topic. It's the interest is just continually growing, and it's really awesome to see. If you could go to the next slide, I wanted to share a high level, 1,000-foot view from our Pathways to Commercial Liftoff report, just generally on the report series for you to know that I think I want to say there's 13 of these now, spanning different clean energy sectors. Most of the clean energy sectors that are attracting attention right now have a liftoff report. The last one released, or the latest one released just last week, was sustainable aviation fuels. So check that out. Go to liftoff.energy.gov for all of the reports. This one, again, was released in March, and one of the things that we're going to talk about in this session is how vastly different the universe is now in November than it was in March, because this is a really fast-growing sector and fast-changing sector. High level, though, I think a lot of the points you'll have heard before, but I'm going to spend a lot of time focusing on our challenges to achieve commercial liftoff and scale, and highlighting for you guys that the definition of commercial liftoff that we use for this report and generally all of the liftoff reports is the idea that this industry would be self-sustaining, would not need further government support in order to exist. That's the goal for liftoff, for commercial liftoff, is a self-sustaining industry. So next generation geothermal has the potential to vastly expand the total resource available for geothermal power generation. We heard a lot about that in the first session. The US has significant and unique starting advantages in the sector. Again, something we've heard about. What we've been seeing since this report's release is that the industry is well on the way to hitting the enhanced geothermal shot target, which we set to be reached $45 per megawatt hour as a national average by 2035. We're seeing evidence of movement towards that direction. Deployment could reach 90 plus gigawatts by 2050, and that, as the cost lowers, that number goes up, potentially up to 300 gigawatts or more, depending on how you see other technologies commercialize. Getting to liftoff, though, getting this industry to commercial liftoff is going to require some work. 2 to 5, what we saw was 2 to 5 gigawatts across multiple states, and somewhere between 20 to 25 billion dollars of investment to get that power on the grid by 2030 in order to reach 2050 goals. Investment is starting to achieve this velocity, but key elements of the capital stack are still challenging to raise. And so that's something we're going to talk about a little bit. And the green and the blue, or red text here represents things that we've seen since the report came out. Generally five challenges: high upfront costs and risks constraining development cycle and limiting geographic reach. That cost is coming down, as we saw. Long and unpredictable development life cycles driven by permitting and interconnection. We already heard about some of the permitting reforms that are happening to reduce the development cycle timelines here, but they are still long. Existing business models that undervalue the potential for next generation geothermal. That's changing with high value PPAs that we're seeing on the market. So a lot of these are there's movement in the right direction, but more needs to happen, particularly the overcoming perceived and actual operability risk for deployments. And only new demonstrations can solve that. Getting more proven geothermal on the grid, and community opposition, which can be solved through many options. And we've seen Forge and we've seen Fervo address this successfully already in Southwest Utah. Next slide, please. Familiar figure to many. This is in our report showing the estimate of the conservative estimate, I would say, of geothermal resource, which you can see the scale is in gigawatts. And effectively unlimited, right? 5,500 gigawatts, and that's only if you're going 8,000 feet down. If you go deeper, it's more. This is effectively an inexhaustible resource that is focused in the western U.S., of course, but there's also a fair amount in the east, and the areas in the middle where you're seeing white. That's not because we don't have any power; it's because we have no data to determine how much power there is. So it's not like there's just a random cool spot in Minnesota. It's an unknown. The next slide, please. As people have talked about this a fair bit, the power demand forecasts have been revised upwards significantly in the last year, and that has just continued since we released this report, driven by large firm power users. So this is a number of electric grids in the United States. The green bar represents what the peak summer demand they projected to be in 2028 in 2022. So this is the 2028 projection in 2022 in dark green, and then in light green was the 2028 projection in 2023. So in just a year, when those should be relatively the same, we saw massive shifts upwards in a number of electric grids, and that's driven by the advent of data centers, of course, but also from electrification of different different appliances, vehicles, and manufacturing. Secretary Granholm loves to talk about the 900 manufacturing facilities that are being brought to the United States during these 4 years, and they are going to need power. And a lot of these places are counting on that. Georgia Power in particular. Next slide, please. This report quantified at a high level the size of the workforce we would need for liftoff and the size of the workforce that currently exists in similar skill sets. That's represented by the gray dotted bar for on the left subsurface operations and on the right surface operations. Subsurface means drilling wells, etc., and surface means building and operating power plants. You can see that the workforce at scale, as characterized by the estimates of employment that we have for different parts of the value chain, in most cases is not as large as the workforce that already exists in largely the oil and gas, but also the electric power sectors. This is an important feature for a fair bit of these technologies where you have to do very little retraining. Next slide, please. Our report used a capacity expansion model out of the National Renewable Energy Laboratory, NREL, to project estimated next generation geothermal potential, given where costs were in 2023 for not just geothermal, but for all technologies to simulate the entire electric grid. At that time, where costs were higher than we anticipate them to be today, we saw a low estimate of about 90 gigawatts of cumulative capacity deployed by 2050, and a fair bit coming online in 2030, up to 20 gigawatts. If you had land restrictions, or it became more challenging to develop solar and wind due to land restrictions, that number goes up to 130. Again, also, there have been estimates since this report that show 3 times this, 4 times this. It is a number based off of assumptions, and this is the assumptions that we had at the time of the report, which I'm going to show you can be addressed. Talking about pathway to liftoff, right? This is what we see as how you get this industry that has a lot of positive momentum, but is facing challenges to scale. And scale we see as the 90 to 125 plus gigawatts across the country. There are three phases, basically. First phase is we need to prove the market opportunity to the folks with the capital, the folks that have the capital to unlock it. 5 to 10 demonstrations in different geologic settings. Expanding that viability, so taking those small places and really hammering in on capitalizing on those resources, and then expanding to new locations in the 2030s, and then in the 2040s, taking this across the United States. When you have confidence in the technology from many times over deployments. All the while pursuing the breakthrough RD&D that got us here in the first place. The kind of work that was done at Forge and supported by the Geothermal Technologies Office and among other places is the reason we get to have this conversation right now. Next slide, please. So what's stopping us, right? What are the enablers? We see that there are 4 areas where you can markedly move liftoff. Cost reductions, which is in green because we're seeing evidence of that happening right now. Large scale demonstrations, which is in red because although there is some demonstrations happening, the expanse of those demonstrations is not at the scale that's necessary for liftoff right now. High value power purchase agreements, right, which is in green because we're seeing those be signed, and community informed siting, which is in black because we don't have too much data on that because the demonstrations across the sector are not there are not many demonstrations across the sector right now to assess. But we'll talk about what we're seeing and where the movement we've been seeing since the liftoff report. Next slide, please. This is a key figure in chapter 2 of our report, which to show some of the physical basis behind cost decreases we're seeing. And so on the left-hand side, you're seeing drilling times at DOE's Forge site. And that is the R&D test site and field demonstration site in Southwest Utah, where you can see at the same site, they're demonstrating a steep learning curve. They're getting better at drilling as the time goes on. And on the right-hand side, you can just see what those average drilling speeds are. Now, in drilling, time is money. The faster you drill, the cheaper your well is. You can see that Forge is approaching high drilling speeds, but not yet was not at the rates that you see in standard oil and gas wells, which are between 120 to 200 feet per hour. So there's room to grow. Next slide, please. This is showing sort of where we anticipate cost reductions to come from, and we've plotted in red here where we're seeing two projects being led by Fervo, Project Red and then Cape, where they plot within this cost decrease. So in 2021, when we started this work, there were the EGS, a greenfield EGS site was effectively modeled to be at a cost, a very, very high cost. In 2023, those costs were substantially revised based off of data we saw in the field, including Fervo's Project Red. DOE then assessed that there was about a 300% decrease in costs that was viable between now and 2035 through improvements in exploration, well and reservoir construction, and power plants construction. And that would get us to about $60 to $70 unsubsidized LCOE in liftoff on the way to our Earthshot target. $60 to $70 per megawatt hour is enough for profitable operations in many locations. And you can see here that what we've seen from Fervo's Tech Day is that they're already approaching that liftoff target, and we would call that relatively ahead of schedule from what we modeled.
But basically where we are right now.
Next slide, please. We talked about the improvements due to permitting. This figure was theoretical when we published it, and now it is much more aligned with reality due to changes made to categorical exclusions adopted by BLM. These changes in exploration and assessment can slice what we estimated to be at least up to 3 years off of your project development timeline. I know that Paul at Ormat suggested an even faster timeline. We're not here to say that's not the case. This is what we were able to identify from our assessments, but the permitting improvements are substantial and can lead to fewer EAs needed, fewer EISs needed, and ultimately faster project development.
Yeah. And
next slide, please. And finally, that second piece, that piece on high value power purchase agreements. You can see in the report we've got several power purchase agreements being signed between 2022 and 2023, and two big ones have been added since. Fervo with Southern Cal Edison and Sage with Meta for 320 megawatts and 150 megawatts respectively, demonstrating the need for firm clean power in these environments. Next slide, please. Investment capital is responding to this movement. The figure we reported is on the left for total investment in the sector, and then on the right, this is what happened in the last 9 months. So we're seeing people respond to this kind of market momentum and energy with increased deal flow. Next slide, and I believe that's the last slide. So what do we need to do now? Large scale demonstrations needs more love. We need more locations in order to de-risk this technology. And we need to make sure that communities are informed and that the locations have the community support so we don't develop backlash. And finally, if we can skip to slide 16, that'd be great. One more. Thank you very much. I wanted to shout out, and GTO is going to go very soon in this. One place where we are starting to get those demonstrations is through demonstration funding from the Geothermal Technologies Office to expand EGS to more locations. And I'm sure they'll speak to that more in their talk. I just wanted to highlight that the department is starting to invest in that space. And thank you very much. I think that'll be all for me. You can go to the next slide. Please feel free to contact myself, Michael.O'Connor at hq.doe.gov, or my compadre, Charles Gertler, similarly emailed at the bottom there. We're two of the authors of the Liftoff Report and would be happy to go into further detail on any of these topics. Thank you so much, and I'll pass it off back to Sarah.
Thanks so much, Mike. I'm glad that your headshot has short hair in it because I've never seen you with short hair in the many years that I've known you. So it's nice to know that it was present one day. I also just can't stress enough how important it is that you and Charles and other authors of Liftoff worked so hard on that report. I mean, those reports are hugely valuable to sort of benchmarking where industry is, where it needs to go. And then even if they become out of date quickly, they're really helpful guides to understanding the path of the industry over time. So thanks so much. I know it's been a huge lift for you all. Lift, no pun intended, but it's a hugely important effort. So our next speaker is also from the Department of Energy. Alex Prisachev is currently the acting program manager for the Geothermal Technologies Office Data Modeling and Analysis team, and she is here to discuss some of the ongoing initiatives that are present at the GTO and beyond. So Alex, over to you. Oh, you're on mute, Alex.
Can you hear me?
I can hear you. It's a little bit soft, but
okay.
There you are.
I'm a bit of a okay. Thanks, Sarah, for all of that. And so my slides, I think, are a good summary of the conversation discussion that's been had today. Some of it I can skip through, but it really highlights the confirmation that all the discussion that everybody's had today and sort of the direction we're going within a GTO. You can go to the next slide, please. For those unfamiliar with GTO, we have 4 main sub-programs. We have our data modeling analysis program, where we're actively addressing non-technical barriers to geothermal deployment. Our low temperature and co-produced resources sub-program focusing on applications for geothermal less than 300 degrees Fahrenheit. Our hydrothermal resources, a group looking at more traditional geothermal uses of hot water, steam, but we are looking at increasing exploration and confirming those resources across the U.S. And then our enhanced geothermal systems subprogram, where we work to advance EGS through R&D, focusing on characterization enhancement and sustainability. Next slide, please. So I just want to touch really high level on our multi-year programs plan. For those unfamiliar, this is a resource that everybody has access to on our website. But if you're ever interested in our vision, looking forward through FY26, it's broken down in these main 6 pillars here, which are the backbone of our multi-year program plan as far as we discussed and planning and funding R&D through the future. And it really helps us. These were all based on technical discussion that was had here today, and really the challenges that face geothermal and its many uses in deployment. Next slide, please. And so again, these were all really highlighted well today. So I can skip through some of these, but in general, here are some challenges that we like to highlight. Technical and challenges including related to hot and harsh geothermal environments. So if we're talking about drilling, production, materials, how they, the lifespan of materials in these environments, inadequate valuation of benefits of geothermal, if we're talking about, to Jeff Tester's point in GHP and heating and cooling deployments, workforce needs that was discussed during the last panel. How do we not only support the needs for geothermal deployment in all of the aspects and needs for workforce to make that happen, but also where we can pull expertise in terms of our oil and gas counterparts with their knowledge in the subsurface. The need for more higher quality data sets and higher resolutions, in looking at ways to better analyze those data sets, permitting timelines, ways that we can look to cut those. We can integrate the great work that BLM is doing on categorical exclusions through exploration for geothermal. And then big challenge is the lack of community awareness of understanding geothermal. We've done a lot in our program in the recent years to address this need, but it's an ongoing challenge that we look forward to talking more about. Next slide, please. Again, Forge, Mike just mentioned a lot, so I think we can skip through that. More information on this is all found on our website. The others here that I don't think were talked about much today is the bipartisan infrastructure law is getting underway, where these projects funded under the bill funding will be looking to explore EGS technologies in new locations, as Mike mentioned, and different geologies. We also are working to improve drilling technologies and time through both the drilling demonstration SPOA that we had that was also mentioned previously, and geothermal energy from oil and gas demonstration engineering program that we refer to as GEOD is looking to address a lot of these R&D challenges, but also workforce needs. Next slide, please. So talking a little bit more about drilling technologies, we recently selected 5 projects that will devise solutions for well cement and casing evolution, which is critical to the challenge I mentioned as far as working in harsh and hot environments. Our geothermal geophone prize is currently supporting the 5 finalists to develop prototypes for downhole seismic sensors, which will collect data on geothermal reservoirs underground. And all of these efforts are making significant technology strides in that are key to helping de-risk geothermal and directly reflection and reducing costs of geothermal deployment. Next slide, please. And wanted to talk a little bit about our grid FOA. This is the first FOA that's under my sub-program for DMA, so it's very exciting, called Grid, where we're looking to decarbonize the economy while supporting the grid. So as Mike mentioned in his slides, we will have significant needs for energy and for data centers and others, looking how we can plug in geothermal to the different markets throughout our country, integrating geothermal into that. Next slide, please. A little bit on critical materials. I think we've talked a lot about this in the past in these forums, but I just want to mention it a little bit in ways that we look as a program to not only explore geothermal, but value-added activities for geothermal. So what I did before on detail, and we'll go back to, is managing critical materials portfolio, where we look to extract critical materials, including lithium and things that will directly support battery deployment in our domestic supply of batteries and energy storage. And so this is just one example that we have with Lawrence Berkeley National Lab, where they were looking at quantifying lithium in the Salton Sea known geothermal resource area. And you can see on the figure here, there is a lot of lithium in the Salton Sea KGRA, and it's enough lithium to support more than 375 million electric vehicle batteries. Next slide, please. So in the area of geothermal data, making data available and a resource for everyone out there, one big thing that we work on with the geothermal data repository, and this is available again to everyone in the public to take a look at. This is an online directory where all of the work that we fund through GTO is stored, and researchers and the public in general can go up there and upload data, look at data, and utilize it. The site was just recently upgraded with all the updates in AI technology. It was updated with an Ask GDR AI tool. And there's a lot going on in changing and updating with new technology. So if you're familiar with GDR, I encourage you to still check it out. There's a lot of new stuff available. Next slide, please. Quickly on this, one thing that GTO is providing data to GDR is on our geothermal community initiative. This is which we support 11 projects to design a community scale geothermal heating and cooling first phase. Projects is currently down selected to move into a second phase, where they'll be providing important data and information about costs and other facets of geothermal community style systems. They also are focusing on a workforce component, which is critical, as we've talk to all the panels today on this. And then communities through this effort will need to form coalitions with partners with 4 areas of expertise. One of these was a partner that knows the community, labor market, and directly help the community as they integrate geothermal into their community. Next slide, please. Geothermal's future workforce, I talked a lot about it through Geode and other things, but one thing that we do directly as a program is our geothermal collegiate competition, where we fund students to do different things. Every year we have a competition, and the theme is a little different. So we support students at all levels and majors to work on geothermal research and solve real-world problems and give them a pathway to clean energy careers by opening eyes to not only geothermal, but getting them integrated into DOE and connected with other resources in the geothermal community. This year, we're ready to launch the competition again, where we'll be working on geothermal heat pumps past prize. And this will be a 3-phase prize where we are asking students to improve GHP workforce pipeline in different regions and communities. Next slide, please. Almost wrapped up here. 2 more things I want to focus on for everybody's awareness is permitting and things that were related to that. So one of the things we are focused on as a program is improving timelines for geothermal permitting that we talked, I think Mike, you mentioned it, and others have significant impact on deployment. So to help to address some of the permitting timeline, we have a permitting task force that includes tribes, environmental NGOs, industry, state, and federal agencies. And through these, we're doing listening sessions, meetings, and stakeholder forums where we gain insight onto the issues that the community is facing with permitting. And we are also working on regularly with other federal agencies like Bureau of Land Management and fund analysis on permitting and regulatory issues. And it's highlighted by the recent work that NREL has done to assess non-technical barriers to geothermal development in California and Nevada. And we have created a webpage dedicated to geothermal permitting, including more information on this in that space. And I think you can skip ahead. Next slide, please. Oh, sorry, the slides are out of. I just discussed permitting, so slide, please. Sorry, those slides were a bit out of order. And finally, I just want to say thank you for having me today, and we are always looking forward to engaging with others and looking for ways to improve awareness and understanding of geothermal. Here are some links that our comms team has worked on putting together for everybody to take a look at on our website. So please go check those out. And if you're at all interested in staying in touch with GTO, we have our monthly drill down newsletter, which has great information on funding opportunities, what we're up to in the future, and some things like that. So thank you. And I will turn it back to Sarah.
Thanks so much, Alex. And if you are on the webinar and have questions about any more of these, please feel free to type them in the chat. Our next speaker represents an NGO perspective, and she is Katrina McLaughlin, who is a Clean Energy Associate in the Energy Program for the World Resources Institute. Katrina has been working on geothermal energy for some time now, and I'm really excited to hear her perspective. So welcome, Katrina.
Hello, everyone, and thank you for that introduction. As Sarah said, my name is Katrina McLaughlin, and I'm an associate at World Resources Institute, also known as WRI, and I'll be talking today about some recent policy developments. Next slide, please. So if you're not familiar with WRI, we are a nonprofit, nonpartisan research organization. We're based in DC with 9 global offices, And we started looking at next generation geothermal about a year ago as part of our work on advanced energy technologies that will be needed to decarbonize the grid. So just a quick note at the outset that our focus is on the power sector, but we do think that geothermal will be important for decarbonizing other sectors, especially industry. And as Sarah mentioned, so right now we have a project underway. It is geared towards a policymaker and NGO audience. So these are not the sort of local community groups. They're more mainstream NGOs that are focused on policy advocacy at the federal level. And the point of this project is really to, understand their current knowledge and perception of geothermal and any top concerns that they might have. The goal here is also to help provide a, call it like a 201 level landscape analysis of what are these next generation technologies? What grid services can they provide? What are the environmental impacts and ways to manage those? And ultimately, how can we responsibly develop these resources? A quick plug that we do have a report that's coming out imminently. Hope it will be out in the next week or so, and then we will have more outreach activities around that. Next slide, please. So when we're starting discussions with these stakeholders, we really start with the why geothermal, why now? Most folks know that geothermal has been a part of the generation mix for decades, albeit at very small amounts. But there have been these recent technological advances, right, that use innovations from the oil and gas industries that could lead to much greater deployment. We also know that, all credible analyses show that in order to decarbonize the electricity sector reliably and affordably, we're going to need clean, firm power to complement the high levels of variable resources like solar and wind. And we're going to need a lot of that clean, firm power, right? There's a few different independent analyses, all came out over the last year or so, that found that the US will need somewhere in the range of 700 to 900 gigawatts of clean, firm power by 2050. So that's a lot. And where is that going to come from? The other sources of clean, firm power. So, thinking here, things like nuclear, hydro, biomass, or fossil with CCS, all of those face their own challenges and are generally at lower stages of commercialization. So the sort of bottom line of our work is that of the clean, firm power options that we have, we think geothermal performs relatively well on environmental criteria and can play an important role in decarbonizing our energy systems. Next slide, please. So I'm not going to go into this in depth. We sort of had a whole panel of experts that were talking about each of these earlier. But what I did want to emphasize for this group is that, when discussing these topics with a non-technical audience, there's a real need for shared terms and relatively simple definitions. This is our schematic of how we bucket out these technologies. And I do hope that this sort of like cartoon version doesn't cause too many of the geologists on the call to cringe. But we really do need some sort of shared definitions and clear, examples and terminology that we can use when discussing these technologies with different groups. Next slide, please. So what are the top environmental issues? As others have said, sort of the high level takeaway is that geothermal performs well on a life cycle basis relative to the other options that we have for low and carbon-free energy. One very clear benefit of geothermal is the low land use footprint. This is, second only to nuclear in terms of land use intensity. And as you might expect for many of the environmental and conservation focused NGOs that we speak to, this criteria is very important. The top concerns, induce seismicity and water contamination. So not really a surprise, but we did want to note that for many of the groups that we've been talking to, water contamination is the top concern and the one that we get the most questions about, not seismicity. So did just want to elevate that is a sort of continued area of concern and a need for more information and education. And sort of on that, oh, sorry, if you can go back. So really wanted to emphasize that having clear information about these risks is imperative. One observation from our research and, sort of being relative newcomers in the space is that there's a real need for updated public-facing assessments of the environmental impacts that are specific for more recent practices in the industry, right? So there's a lot in the literature on conventional hydrothermal, and some of that might include some of the older EGS projects, but those studies are over a decade old at this point, and they don't reflect the just, sort of astronomical advances the industry has made over the past few years. We, of course, also have a lot and sort of, the general literature about unconventional oil and gas development. But we really think that there's a need to have some clear public-facing information on how the drilling and completion techniques used in oil and gas context are both similar and different in the geothermal context, and how those might change the risk pathways. And did just want to do a little call out that one of the recommendations that we have in our report is actually to commission some updated analysis that's looking at this, including potentially done by the national academies or some of the national labs, to help reduce some of these, again, sort of accessible to a more general policy audience, not necessarily the academic or industry audience. One other takeaway for us is that, of the groups we were talking to, they're not a monolith, and there certainly are differences of opinion. But the folks really did recognize a need for clean, firm, dispatchable power. There was a lot of interest in understanding more about these new geothermal technologies, precisely because, I think a lot of people recognize the need for these types of resources, just the changes we've seen over the past few years in terms of electricity demand. A quick, important caveat though, of, they're interested, but they have questions. Really, again, just underscoring that need for information that's accessible to a general policy audience. What are these technologies? What are the practices used in developing them? Being really upfront and transparent about the risks, providing information on hydraulic fracturing fluid composition, on any chemical sealants being used in well bores, data on water use across the project life cycle, things like that we think are all very important. Next slide, please. So going to be very brief on this. These were touched on sort of throughout the day. Geothermal, certainly, it's an exciting moment in the industry. There's a lot of potential, a lot of really big recent advances. There still are some key barriers to scaling. Mike obviously spoke about these in great depth. And also just want to also commend the Liftoff report, a sort of fantastic piece that came out earlier this year. So the sort of top three barriers that we focus on in our analysis, that need for upfront finance, right? Capital intensive, requires a lot of capital early on in projects, the permitting process and associated timelines. Also just want to note that, while many energy technologies might face similar challenges, it really feeds into that first barrier of finance, right? This is a capital intensive emerging industry, and uncertain permitting timelines can make that financing even more challenging. And then finally, next generation geothermal it's an umbrella term. It covers many different technologies that are at very different TRLs. And so the policy solutions here will not be one size fits all. Next slide, please. So we, sort of see a need to invest in next generation geothermal across those different stages of technology readiness. We have here a sort of menu of different options that, can help meet the needs of technologies that are in all those different stages, right? Those that might still be in basic R&D, to also those that have successful commercial operations. And as Tara noted earlier, geothermal industry has not gotten the same level of support that other clean and low carbon energy technologies have. Next slide, please. So what might be on the federal sort of policy horizon to help address some of that discrepancy? A pretty, obvious note here that there will be an administration change next year, and I am certainly not going to try and, read the tea leaves of what's going to happen. But with that said, some of the recent priorities that we've seen in DC can help indicate where we might see some action on geothermal going forward. So, very importantly, geothermal is included in the tech neutral clean electricity tax credits that were part of the IRA. We had proposed regulations and a comment period on that earlier this year. We're still waiting on final guidance from Treasury on that, but we do expect it by the end of the year. And then, something that's important to note is that geothermal is sort of one of those rare energy topics that does receive some bipartisan support. There's listed here a couple of the bipartisan congressional bills we've seen over the past year. A lot of this focus, that's sort of like alphabet soup of acronyms there. All those bills are on permitting reform. But then there is also, as was discussed, the supercritical geothermal R&D bill. There's also been, moves to increase funding to USGS for updated subsurface mapping. And then not on the legislative side, but more on, sort of agencies. looking ahead to next few years, if we, we might see more action on things that are trying to increase energy production on federal lands. And, that obviously would impact geothermal. About 70% of geothermal currently happens on federal lands. So any moves there to say, increased lease sales or other actions from agencies might impact geothermal. And then, as others have said, BLM has a proposed categorical exclusion for geothermal resource confirmation activities, and the comment period for that closes tomorrow. Next slide, please. So this is the final slide for me, and wanted to end with it's not all about federal action. There's also a lot of momentum that is obviously happening at state level and within the private sector, and we've heard a lot about that from other commenters today. This slide is just a little bit of a potpourri sampling of some recent developments that we've seen that I think are particularly notable. The first is some procurement requirements through state PUCs as a potential area of action. And that really gets back to what, many others have been talking about today in terms of the increasing electricity demand. All of those three sub-bullets there, they're all from the California Public Utilities Commission. And I think really just illustrate not only the scale of the need, but also how quickly this context is changing year over year, right? You have a procurement order and then it's updated in just a couple of years. So there's really just a lot of change happening in this space. And that last bullet, we'll also note, the first two were on procurement orders for load serving entities in the state. And then the last one was a result of legislation this past year that authorizes centralized state procurement of these clean firm and other resources, including up to 1 gigawatt of geothermal. So just, different levers being pulled at the state level. State legislation and support for geothermal is increasing, right? So we're also seeing financial support coming not just from at the federal level, but the state level, like Colorado, New Mexico, others have these tax credits and grant programs out. Did also want to call out this piece of legislation from Washington that was enacted this year, where legislators there said, we want to encourage more geothermal in the state. And so they did sort of a number of items. They updated the leasing program on the state land, on state lands. They improved subsurface data availability. They provided exploration cost sharing program. And very importantly, all of that was linked to improved induced seismicity hazard analysis and management. So we think that is sort of an interesting bill that we saw at a state level this past year. And then going to end with, as others have said, a lot of action in the private sector, obviously, including some innovative offtake arrangements. Wanted to highlight this clean transition tariff out of NV Energy and Google. So under this proposed tariff, Google will pay the difference between the cost of geothermal and the lower cost resources like solar and natural gas that the utility would have been obligated to go with under least cost restraints. So basically saying, this type of clean firm power is important. We'll pay the price premium. We'll get that fixed rate, and then we'll get credited for that energy and help avoid some of the fluctuations from prices and demand charges, things like that. So really exciting developments happening across private sector, state policy, and then of course expect there might be some things happening at the federal level as well. With that, I think that's it for my time. So happy to hand it back to Sarah.
Thank you, Katrina. That was super comprehensive. And I like how you dipped into state action as well as federal action, because there's a lot happening on the state side. Also, an interesting note about demand side support in addition to supply side support that maybe we'll get into in the Q&A. So our next speaker is Christopher Catisse, who is the Project Marketing Communications Specialist at Utah Forge. For those of you who are not familiar with Forge, Forge stands for Frontier Observatory for Research in Geothermal Energy, and it is a Department of Energy backed field laboratory in Beaver County, Utah, southwestern Utah, that is developing, testing, and accelerating breakthroughs in geothermal energy technologies. So Christopher has led many of the marketing, communication, stakeholder engagement efforts at Utah Forge. I have been a student of his, and I'm really looking forward to hearing his take. So over to you, Christopher.
Well, thank you very much, Zora. I really appreciate it. Can we go to the next slide, please? Are waiting to find me? Can you hear me, Sarah?
Yes, I think
There we
Ryan's
Terrific.
catching.
No worries. So, as my friend Sarah mentioned, that what Utah Forge is, I wanted to give you a little bit of an idea of where we're located in southwestern Utah. So we're 10 miles from the nearest rural town called Milford, and that's about 205 miles southwest of Salt Lake City. Just to give you some comparison, the 7,400 people who live in Beaver County are located in 2,600 square miles, whereas the 1.2 million of us living in Salt Lake County are in just 740 square miles. So Beaver County is incredibly rural, a lot of spaces out there. And in fact, they ranked number 24 out of Utah's 29 different counties. Next slide, please. So we thought we'd talk today a little bit about the best practices we see in the outreach and communication efforts that we've realized here at Utah Forge. And the first step is a dedicated outreach team. These are the folks who are on the ground that oversee the day-to-day interaction. They're recognized by the members of the community. They're available for the community to answer any questions or raise any concerns with. That is, for Utah Forge, myself and my colleague, Gosha Skovram. So they need to be diverse, and not just we have a man and a woman, but diverse team members, because people have different skill sets. So backing us are scientists and our student interns, as well as admin and financial support. We also have found a great deal of success collaborating with other parts of the University of Utah, as well as different colleges, and we will talk a little bit about that later on. May I have the next slide, please? Thank you. So I am always asking people, who is our audience? And for most of the projects in geothermal world, recognizing your audience is incredibly broad, is vital. It's not just the folks in Beaver County. It's not just the folks around your project. It is wide and deep. And that fosters support that is equally wide and is equally deep. For Utah Forge, it spans everyone from the general public and students to elected officials, environmental groups, and of course, our friends in the media. Next slide, please. It doesn't really matter who your team is if you're not presenting a transparent and consistent message across the board to every member of your audience. Because if you are not telling your story, someone else will tell their version of it for you, and you clearly don't want that. That's why being consistent and transparent is so important. So whenever we have news or an update, we strive to ensure that as large an audience as possible can stay informed about that activity. And it doesn't matter whether it's legislators or grade schoolers. And in order to communicate with those different communities in the way that best suits them, we have developed a whole slew of mechanisms to communicate with them, whether it's our website or social media or webinars like this, to media relations, and my favorite, and we'll talk about it in a minute, in-class visits. The whole result of that is that you are controlling your narrative, and the community knows what's going on, and they feel empowered, and they feel a sense of ownership of the project as well. Next slide, please. So K through 12 is so much fun. Unfortunately, studies have shown that younger generations are dealing with what's called eco-anxiety around the climate crisis. Going into classrooms helps students understand what geothermal energy is and its role in addressing that crisis. Hands-on activities like modules and games, they make learning fun. In turn, those contests and activities are discussed with parents and siblings back at home and grandparents. We've held song parody contests for older students that span the state of Utah, and we have a Beaver County specific poster contest for grade school students. And we go in, we talk a little bit about geothermal energy at an age appropriate level. We do some fun science with them, and then they do a poster about a topic around geothermal energy. And it's important to note that those posters are then displayed in the local public libraries. There are 3 cities in Beaver County and all towns, and all 3 of those have a public library. And that draws people in so they can see their kids, their nieces, their nephews, artwork, whatever. And they too learn a little bit more about what we're doing and about geothermal energy. We regularly attend STEM Fest, which brings students from around the state to a 2-day conference where they get to stop at different booths and learn different types of STEM issues. Although we had to skip this year because of scheduling issues, last year or 2 years ago, I guess, there were 14,000 students who came through our area during the 2 days. This outreach builds understanding about geothermal, not just immediately, but for the generations to come. And I like to joke only half-heartedly that 100 5th, 6th, 7th graders in Beaver County could probably tell you more about geothermal energy than the 100 members of the US Senate. But along with building that understanding, it also reduces eco-anxiety. It's also, as I mentioned a little earlier, it's important, next slide, please. It's important to have transparency. So we regularly, on at least a quarterly basis, update the Beaver County Commission and the Milford City Council about our activities and our planned activities. We are very transparent about induced seismicity. And although our particular site is aseismic, the state of Utah is very seismically active, right? So we talk a lot about it. We explain the difference of induced seismicity and an earthquake that happens because it's happened. These meetings are all public. We advertise in the local paper so that the public is alerted to attend and they know that they can ask questions of us. Sometimes they want to stop afterwards and spend a couple of meetings. We also have held field trips for key stakeholders out to the site. Now, along with that seismic conversation, we want to make sure that people understand what's going along with it. So we have equipped the 3 local libraries with computers where residents can actually check in real time any seismicity that's happening. They can do it at their own homes as well, but we want to make sure it's available to absolutely everyone. And like Katrina mentioned, most of the questions we get are not about seismicity, but they are indeed about water usage. And one of my other favorite parts is that we are a mainstay at the county fair. As you can see, the picture there, kids love coming and learning and playing games with us. And I have to say, it makes us part of the community as well. All of this builds trust with elected and other officials, which is important, but more importantly, with the public. And in my opinion, this transparency helps turn potential NIMBYism into what I have coined as YIMBYism, yes, in my backyard. Next slide, please. So as important as Beaver County is for us, we also recognize that there are many key stakeholders who are hundreds of miles away. So in order to reach them, we outreach to the University of Utah students, for example. We've held field trips for elected state and federal officials and other folks in the energy world. The president of the University of Utah has been there. And we actually even had a media day, which was incredibly successful. As I said earlier, we work closely with other departments and colleges at the U and other universities. So it started with a capstone course talking about EGS and seismicity and how you communicate that here at the University of Utah, which led to a region-wide public survey. And along with our friends at Utah Valley University, working together with the U, a nationwide survey that was recently completed talking about geothermal awareness, EGS awareness, seismicity versus microseismicity, all of the ideas being what do folks already know. We work all the time with the University of Utah's own marketing communications department that helps spread the word and lets the campus community know about what's happening with one of, if not the largest research project the University of Utah has ever received. And we are a top tier research university, so that's very important. And in fact, in the bottom photo there, that's during Welcome Week on campus, and the man standing next to me with his tie is the president of the University of Utah. So all of this outside Beaver County outreach results in broadening support and raising global awareness about geothermal energy. Next slide, please. So what are just some of the lessons learned to take away from my brief time here? Well, don't limit yourself to older students who have greater backgrounds in earth sciences, like high school kids. Younger students are excited about this topic. Number two, everyone enjoys interactive modules. It doesn't matter if they're a kid or they're an adult, and they are a great way to break the ice and start the conversation, and they make science fun. Thirdly, consistently participating in local events helps the community see you as a part of it and your project as their project too. This past summer, we were doing some meetings, and Gosha and I had to stop off at a gas station. There were 4 little girls eating ice cream at a table there. And as I jumped out, they said, "Hey, you're the geothermal guy." And when Gosha got out of the car, they said, "Hey, you're the other one." Gosha's not a guy, for the record, but it is that ownership. It is that encouragement of YIMBYism. Fourthly, keeping the community apprised of the project and its successes is invaluable. And using local businesses like hotels, restaurants, cleaning crews, that all fosters that sense of pride and deepens the support. At the fair, we had people, teenage boys come up and say, "Oh, over the summer, I worked with company ABC and built the fence around those wellheads." Women came up, or people came up with their kids and said, "Hey, remember when mom was cleaning those trailers? That's where it was at this research group." So it does give that pride and support. And then finally, people in general are really excited about the potential of geothermal energy. So don't exclude anybody that you might think won't be your audience, because they probably are. Last slide, please. I just wanted to thank the National Academies for including me. I also want to thank the Department of Energy, who funds us, as well as the Utah Trust Land Association, the BLM, everyone here at the state, and our neighbors like our friends Fervo for all they do for us and with us. But I want to say we are forever grateful for the people of Beaver County, for their friendship, their cooperation, and their support and their understanding. One of the greatest compliments our team ever received was a couple of years ago when a member of the Beaver County Commission said, "Gosha and Christopher are 2 of Beaver County's own." And that said it all. Thank you all very much. And you've got my contact information if you have any questions. Thank you very much.
Thank you so much, Christopher. Okay, so for the next, we have half an hour. And so for the next half an hour, in addition to sort of looking at the Q&A coming through, I'm going to ask a couple more open-ended questions, and I won't initially direct them to panelists unless you all don't speak up, in which case I will call on you. Am I breaking up? I'm worried about my internet connection. No, okay, great. I'll just keep going as is then. Okay, so we're gonna dive right in. Katrina mentioned that 700 to 900 gigawatts of firm clean power will be needed in the US by 2050. So I'd like to throw out to the panelists and ask you, what's your perspective on how big a role geothermal will play among the technologies that Katrina listed? She listed nuclear, hydro, gas with CCS, biomass with CCS, those types of things. And I really would love for all of you to sort of talk your book and talk about what your perspective is on how big a role geothermal will play in that large tranche of new gigawatts, and then what the most pivotal things are that need to happen to unlock that potential.
Well, I can start with the observation that I think if any of us knew, we might be compensated handsomely for it. I certainly don't have the answer to what exactly that generation mix is going to look like. But I will say that from the studies that we've seen, one of the main observations about geothermal is it depends on what constraints are on other technologies, right? If we have a lot of constraints on siting solar and wind, that increases geothermal. If nuclear has trouble, either commercializing those advanced reactors, getting licensing, and maintaining existing reactors, that impacts geothermal and the need for other clean, firm sources. I think the similar thing can be said about CCS, about hydrogen applications in the electricity sector. So my maybe it's a bit of a cop-out answer of we don't know, but it's all of these things sort of operating in tandem, and what are the different policy, regulatory, market constraints that each of these face?
Yeah, I think this is a great question, and also there's going to be an element of all of it. Energy is local, and there are some places that are just really well suited. Like if you ask me about the Gulf Coast, my other life is CCS. The Gulf Coast has pretty great infrastructure already set up in terms of pipeline right-of-ways, in terms of carbon storage, in terms of the things that you need to put CCS in a lot of those places, and it can commercialize pretty well. But also, geothermal has the advantage of I think geothermal and nuclear both have the advantage of not requiring this additional set of infrastructure that CCUS might require, or that hydrogen might require, or even new hydropower. You need the infrastructure around building out the dam system. So there's a major benefit to that that makes us optimistic of the potential. I will say right now that the Geothermal Technologies Office grid FOA, the Geothermal Resource FOA that's trying to quantify this, is really sorely needed, because the modeling tools that we've been able to use to try and highlight the potential of this technology all run up to this this challenge of picking the least cost option, not considering the value of energy at a specific time, right? So power at 3 p.m. is more valuable than power at 3 a.m. And that is something that very few models out there. I know that the Princeton folks can do this. Not that many other folks can. And our ability to communicate the value here is inhibited by that lack. And I'm glad that GTO is investing to try and improve that capability. Yeah, I think that there's a lot of advantages around the lack of additional infrastructure that puts geothermal somewhere really promising.
Yeah, Mike, you took stole my thunder, but yeah, I was going to mention the grid flow in particular. At GTO, we're very aware of these needs. Mike, in your presentation, you showed the growth need in different regional utility sectors, the need for power is enormous, and where power is coming from is important. And geothermal is, as we all know, untapped in many of these regions. And one thing that the Grid FOA is looking at with our its recipients is how we can adapt geothermal in these very varying markets, and not looking to offload one or the other, but we're going to need to meet those power needs very significantly, and we're looking to figure out how to do that with geothermal.
It is really interesting because I feel like geothermal often gets compared on an LCOE basis to other renewables. And what's interesting about that is while it values the levelized cost of electricity, it doesn't value capacity factor. It doesn't take into account timing value of the energy resource. And so I'm really looking forward to the outcome of the Grid FOA as well, and just generally more metrics that sort of measure the value of geothermal energy and other firm clean resources on an apples to apples basis. Christopher, did you want to add, or shall I move on to another question?
No, I think everything was being covered. Thanks, though.
Jeff Tester, did you have a question?
Yeah, actually, this gets a little bit away from this very interesting session, Sarah, but I'm kind of curious since we have two DOE people here. So the GeoVision study is obviously something you guys have put out, and I'm curious about how realistic do you think the potential things that are talked about. And I'll give you an example, getting a little away from electricity for a minute. And I'm reading from the summary of the report, Michael, et cetera. So it says that in order to kind of reach this potential, you'd have to get the 17,500 installations for direct use versus the 21 that we have, which are pretty tiny, as you guys know. So how, and this is by 2050. So we got 25 years left. If you had to make a prediction, will we be looking back at GeoVision in 25 years and be disappointed? Or is there an issue that, you know, I understand the limitations you guys have, but is this something that you need a more level playing field within the department to make this happen? Versus, and I know it's a tough question, but I'm just curious whether you have a current view on that.
Well, I don't like making predictions.
Right, nobody does.
I don't know that. But I will say, and this might be, you know, the GeoVision was written with these assumptions in mind.
Right.
And I think going forward, as technology is adapted, as regulation changes, as people are, you know, we have oil and gas really heavily investing in geothermal. And as we're making, you know, as industry moves on, things are changing. And so what the GeoVision says was our best guess and assumptions at the time. And as new things come online, new investments, new regulatory and policy changes, permitting timelines, it all goes into a greater adoption of geothermal across the board, whether it's DDU or EGF. So I can't predict, but all of these things are going to lead to more adoption and deployment of geothermal.
Right, I agree with that totally. I was just kind of curious whether they're, given there's, you know, that's been some time since that report's come out, and we've had a few things that have interfered, a pandemic and a few other things that have interfered with progress, but that's a pretty big bar to raise. And electricity also is pretty big. And I just would hate to see us becoming disappointed, because it's not, to me, limited necessarily by technology here. It's more by what the investment would be. Policies are part of it, but is it something that you would feel that is going to be looked at again seriously in the next few years?
So Jeff, you're prompting a release here that we can tease here, but we're not certain on the liftoff. The liftoff report for power is going to be accompanied by a liftoff report for heating and cooling in the upcoming weeks to months, and that's again a collaboration between many offices of the Department of Energy, some of the commercial focused offices, along with GTO on the R&D side, to get at some of these questions. And yeah, this will be 5 years since the GTO analysis was originally done. So we're really glad that we're being able to get that out. But I think that For the first time in a long time, and I've been at the department for 4 years. Alex, I think you've been here longer than I have, but I think
Right.
we are no longer clamoring inside the building for equal representation.
Great. Well, that's great to hear.
Geothermal is
Right,
getting
right.
a lot of play here in the building, and it's I think a direct result of the market demand and also the successes that we've seen.
Right. So we want to help as much as we can. This is not meant to be an embarrassing question. It's more realism. You know, you've got a lot of challenges ahead of you for sure, but I'm glad to hear you optimistic. So that's thank you both, Alex and Michael.
And I am slightly hesitant to try and describe the results of an academic study to the committee at the National Academies on this, but I will just note that from sort of our audience, the Algebron and Horn study, study that came out earlier this year, right, that showed sort of increased potential for EGS and at lower LCOEs than previously thought, using some of the advanced drilling rates that we've seen from Forge and Fervo and others over the past few years. So wanted to just underscore that, you know, the rate of advancement that we're seeing in the industry of, you know, the NREL ATB is already being out of date. Just the level of advancements are happening with the level of advancements that are happening in the industry. So, you know, again, crystal ball is hard, but to ask whether, you know, the GeoVision from 2019 is still on track, I think just the level of advances we've seen over the past few years make that a hard question to answer. I also see Tara just raised her hand. Apologies, Sarah, that might be.
Well, I'm really glad that you commented on that, Katrina, because I'm holding myself back in my moderator capacity, but I was really going to talk about the pace of innovation as well as sort of outpacing our predictions. Tara, do you want to jump in here? Something new or something to add?
It is a question for the team, if you don't mind.
Yeah, go for it.
I'm interested to hear your perspectives on how we might work in sort of public relations internationally around just this is both on the heating and cooling side as well as the power production. Do you see opportunities for joint investment? Do you see other opportunities for, we'll just call it through the various banks, et cetera? What are you guys hearing? Is there an opportunity for us to lean into that space as well to help learn and share faster?
Christopher, do you want to head us off there?
Sure. I actually do think that there is a great deal of opportunity. Again, overall geothermal. We were approached at Geothermal Rising recently by some folks from Great Britain asking about how we might be able to collaborate with them. Sharing of knowledge, and somebody said that all of the data that Utah Forest produces is free and public to everyone who uses it, which is fantastic. But that is a great tool to use. There are best practices or best practices or best practices, whereas perhaps if you're in the UK, you're not going to have the audience of an indigenous tribe like we do. We have the Paiute Nation in Beaver County, but you're going to have your own issues to deal with, but you can still learn from each other. I think that the opportunities are vast.
I can say from maybe a DOE perspective, we have a lot of folks from international communities really interested in geothermal and adoption through all flavors of geothermal. And some of the things that feedback I get to Christopher's point, it's, a lot of people are experts, and they're experts in their own backyard in the subsurface. They're geoscientists and engineers just like we are. And it's not so much understanding the geology, it's really they need that industry understanding and how they can deploy geothermal quickly, efficiently, and how to do it with their regulations and policies that they deal with in their own country. And so I think that professional expertise is needed throughout through the world and in all the various markets for geothermal. So I think there's a big place for industry to play in this role.
Well, I mean, most of the investment in the sector right now has been from industry, right? The United States federal government's total budget for Geothermal Technologies Office is 130 million a year or so, give or take. I'm not sure what the exact number is right now, but there's near almost $1 billion in the market right now, right? And so most of that is not the U.S. government. We're already in that space, and the U.S. government can, I mean, I think our liftoff report shows that, can absolutely catalyze certain parts of the capital stack where the private sector is unwilling or less willing to play. But these entire systems are going to have to be, as Jigger Shah loves to say, private sector led and government supported or government enabled.
I mean, if I may, what Alex said was spot on about knowing your audience. The issues that are raised in Beaver County, and Sarah can join me with this, are going to be very different from the issues that might be raised outside of Houston, Texas, which are going to be very different from the issues raised in France or China or wherever. And having that understanding and learning from each other, I think, breaks down those barriers.
Okay, great. Doug, do you want to jump in?
Yeah, I want to pull on this a little bit. And it goes in the direction of the investability of the sector. So one of my questions is, and I guess it may be one of these projections, how long is it going to be until there are 10 fast followers to Fervo and 5 major super hot, small, companies capitalized sort of at the $400 to $500 million range? Because I get, a lot of the dialogue today has been around the attractiveness of the sector. The costs are coming down, the LCOEs are attractive, the PPAs are going up, and so all the pieces are sort of aligned there, but the activity is not really showing up at the pace one might expect. And maybe for me, another way of asking that is, coming up in, I think it's in January or February, is it's a gathering in Miami. It's a sort of I think an annual thing. It's called Mines and Money, and it's basically where the investment community comes and meets the mineral sector, and they do deals. And it's how far are we from this transition from government funded projects and basically liftoffs and all the work that's going on in the private sector to where we see that jump in that curve, where we see it as being seen as a really, really attractive investment opportunity?
Whereas I can't really address the actual investment side, I can tell you that 5 years ago, when I started working at Utah Forge, it was us by ourselves out in the desert. There are now, along with for 2 other companies that have leased the land all around us. So people are seeing some degree of investment and wanting to do it. Whether it'll be on a scale like mines, I can't say to that, but we are seeing people move into that area, which is good for the county.
Yeah, Doug, I think there's a multifaceted answer, and I think the best person to answer this is probably Sarah on this panel. But we've had a lot of conversations from our side on this exact question, and I guess my short, relatively cheeky answer is when it's not as hard as what Fervo is doing. Fervo's taking a lot of first mover risk in a couple of places. 2 that I'm thinking of right now are the high upfront cost of appraisal of a site, right? Of getting a flow test done. That's tens to $100 of millions that has still a perceived risk level that is high. There's a relatively small group of people with both the capital and the knowledge to be able to bridge that gap right now, although it is growing. We're getting more responses in for FOAs around that sector, and so there's some movement on that front. And then the other side is seeing just supply chain constraints and development constraints that comes from being first. No one wants to be first. As Chan says all the time, there's 6 people in line to be 10th. But no one wants, it's not just that no one wants to be first, it's that a lot of these no one wants to be in the first 10. So I think that the faster we can get some sort of catalytic capital to get appraisal, to get that hard to raise money, this is why we made it our liftoff criteria. 5 to 10 locations. The fastest we can get to that is the fastest we'll see lots of fast followers, because what's happening right now in the market for not just Fervo, but also for Ever and for Sage, is what they're doing is really hard.
Yeah, I think a lot of it comes back to building trust. I think it's hard to fight against historical headwinds for an industry that just hasn't grown really meaningfully, really quickly. The costs haven't come down over time. And I think that is a conversation that we at Fervo didn't expect to have over and over again in financing discussions, how the problem is not actually with us or our technology or our performance. It's how maybe the industry has performed or hasn't performed to date, or has grown or hasn't grown to date, or the contracts it has or has not signed to date. And that is providing more of a headwind to the industry. So I do think we are at a pretty pivotal time for trust building in, policy realms and financing realms and stakeholder realms, in off-taker realms. And I think the more that we can have successful projects, the better. And so I think when we see competitors of ours sign commercial agreements and start to break ground on projects, it's really exciting for us, because unfortunately people do have to move first to build trust. I think my maybe last question here really revolves around building trust. And I want to ask the panelists, Christopher mentioned that the stakeholder audience is both wide and deep. And I think we have found that too, because we are trying to address all of these audiences anew. It's not just the local stakeholders, but it's policymakers and people in finance, people who've never done this before. It's supply chains, customers, all sorts of people. I kind of feel like we're at a pivotal time to redefine the narrative around this industry. And I really want to know all of your perspectives on what the industry needs to do right now at this time to build trust in that wide and deep audience base. And I know that's a broad question, but I thought I would throw it out there and see what you have.
I mean, I'll start. How's that?
Great.
Transparency. You need to have honest and frequent conversations about what is going to happen, what could happen. As I mentioned, the folks in Beaver County, they heard a lot about seismicity and that we were going to induce seismicity, but they also know that we have a traffic light system, right? And I think really making it part of them is important, right? So we speak, like I said, we spoke with the Paiute Nation recently, and now they are looking into potentially drilling their own electricity EGS system on some Paiute Nation land, which is kind of interesting. Being forthright, you can't go wrong with being forthright.
And I can speak to, I know I mentioned a little bit critical materials, and it's a little bit tangential to the conversation we're having today on geothermal deployment. But so in terms of critical materials and the work that the Lawrence Berkeley team did, that mentioned in my slides, if anybody's interested, the community outreach aspect of that project in the Salton Sea is one of the largest, I think, in GTO's history that we've done to date. And one of the biggest components, and Christopher already mentioned this, but it's really community engagement and being in the listening seat. In terms of critical materials, it's, not just dealing with regulations and state level government and federal government. It's, these communities, people have come in through the years in the Salton Sea saying they're bringing jobs, they're, wanting to develop Lithium Valley and all of these promises. And when you're living there, living maybe under the poverty line, and you hear these messages, and maybe you don't, you've heard of geothermal, you see it every day when you go off to work, you understand it. So like, what does it mean to me when people are going to come in and develop lithium from my backyard? What does that mean? And what am I going to do to benefit from that? And we've not historically done a good job or been able to really focus on that community engagement piece through the work that we do. And it's been such a valuable thing and much needed to have that open communication and really just being in that listening seat, providing information to people that might not understand geothermal or understand critical materials and what it's going to do to them, and being sort of that, in terms of the Salton Sea and Lawrence Berkeley, sort of being in that middleman seat for what is industry going to do for this community. And I think really helping bridge that gap has been a huge benefit in building trust with researchers, but also industry that's operating in their neighborhoods. So yeah, listening is a huge piece that I think can't be understated.
And I think that's really incredibly important. Unlike our friends at Fervo, we don't generate a lot of jobs at a research site, right? So we make sure that we do eat at restaurants, that we do stay in the hotels, that we do hire locally. We have an account at the Ace Hardware, for example. And we're not terribly shy on telling them, periodically how much money we've invested and we spend in their community, because that's the federal tax dollars coming through us, but going back to the taxpayers and that community. And it's incredibly helpful to them as well. So don't be shy.
I think one of the things we're learning in OSED, and one of the things that this is also echoing, is this is a manpower heavy task. This is a lot of face-to-face time with a lot of people, thousands of people having thousands of conversations over and over and over again. This is not something that can be done centrally from DC or from anywhere where there's a company HQ. OSED is having that we incorporated the community benefits plans into our project merit review scores because it is a business risk, right? And so they need to invest in mitigating that business risk through community benefits plans. There is no shortcut. I also think that there's folks who say that early engagement can be dangerous because you don't want to talk about a project before a project exists. I think that there are in some cases, you can frame it in a way that can scare people, but early engagement on a technology and on an approach, not hiding the ball, largely provides folks with the ability to make more informed decisions when the time comes for a project to show up.
Yeah, underscore everything that folks have said, and really wanted to again emphasize that need for transparency around risks and environmental practices. Folks on the call will know more about this and are doing those face-to-face meetings. But that's something that we see is really key. And right now, just where the industry is at, I think we talked earlier about the risks of being a first mover and everyone wants to be 10th. But there's also, the sort of questions of what happens when this industry is scaled, and do we have the appropriate environmental safeguards in place? The DOE induced seismicity protocol has been very successful, but it's right now it's only required for federally funded projects, and then for falling voluntarily. What happens when the industry is scaled? Is there a need to require something like that induced seismicity protocol at the state or other levels? And then I also kind of wanted to, fall back sort of the misinformation came up earlier, or, misunderstanding about some of these practices. And while I think it's true that geothermal and oil and gas industries are very different in terms of their structure, in terms of their incentives and production lifelines that will change operations, a lesson for at least me from an NGO perspective, is that the early experience with unconventional oil and gas development defined the industry for the next decade. Right now, I think the Fervos and the Evers of the world know that they are getting the social license to operate for the entire industry in the US. But making sure that, those best practices continue once the industry is skilled, is something that is of, concern, not just for environmental and safety protections, but, for this industry to continue to grow and continue to operate. So.
Man, I so thank all of you for having really great and thoughtful responses to that. I think as an operator, it's really top of mind. And while we also believe that transparency is the path to building trust, transparency can set traps for you as an operator. If your project A does not have the water loss that you are hoping, and your project B has a 50% improvement in water loss, and you expect your project C to have 100% improvement in water loss over that, you can end up in a pretty challenging place by publishing results from project A. And we have definitely had that experience, and I think we've decided to move more in the transparent direction than against the transparent direction. But it is an interesting place to play. And I do think Katrina regulations, as you said, are really pretty meaningful at this point in time. I think we should be regulating induced seismicity in the US to ensure that everyone is sort of required to do the same monitoring and reporting, so that, no one person sort of sinks the social license to operate for everyone else.
If I can hijack the last 30 seconds and think of it right back to you, I did want to say, for us, it's always important the relative to what. It's the relative to the other generation sources that you would have in the mix. And so when we're calling for updated analyses, when we're calling for transparency, it's always not next generation geothermal in a vacuum. It's relative to what. There's this increased urgency for new carbon-free energy sources. How can we responsibly develop them? So,
awesome. Well, thanks so much to all the panelists for being here. Thanks to the panelists from the last panel, and to all committee representatives, and to all audience members. It's been a great discussion and a great day. I think we had over, nearly 600 registrants for this. And when we arrived, saw a few hundred people on the line. So it's been a great day, and we really appreciate all of the interest that all of you have shown. I think that I am on the hook for wrapping this, so I'm going to let you go. We will be posting a recording of this event within a few days on the Community of Earth Resources website, so you'll be able to find it there. Also, feel free to follow up with any of us should you care to do so, and have a great rest of your day. Thanks so much.